At the very beginning of time, there was nothing at all. There was no matter and no energy. There was complete emptiness. Then, in an extremely short moment, this emptiness changed into everything that exists. Space appeared. Time started. Very small particles moved outward, and from them the first forms of galaxies, planets, and life eventually developed. How could something as large and complex as the universe come from a state with no matter or energy? How did a state with no activity give rise to the Big Bang? How did nothing produce the beginning of the universe? Before we begin this video, subscribe to our channel and let us know in the comments below where in the world you're watching from. We're always eager to hear where our viewers are tuning in from. The idea of nothing may sound simple, but in reality, it's one of the most confusing and mind-bending topics in all of human thought. For thousands of years, from the time of ancient thinkers to the age of modern science, people have been trying to understand what nothing really means. And as strange as it may sound, the word nothing doesn't have just one clear meaning. Its meaning changes depending on who's using it, whether it's a thinker, a scientist, or even a physicist working on ideas about the birth of the universe. Especially when we start asking what existed before the Big Bang, or how everything could have come from nothing, we first need to understand exactly what that word means. In thinking, nothing is usually taken to mean complete non-existence, the total absence of anything at all. No matter, no energy, no space, no time, not even empty air or unseen forces, just nothing. This is not an easy idea to understand because we have no experience of such a thing. Even what we call empty in daily life, like the air in a room or the space between stars, is still filled with gases, tiny bits, light, or unseen fields. Take the ancient Greek thinker Aristotle, for example. He lived over 2,300 years ago and said that a truly empty space could not exist. He believed that nature disliked a vacuum, and that all space must be filled with something, even if that something was unseen, like a kind of thin fluid or mysterious ether. His ideas were partly a response to earlier thinkers, known as atomists, who believed the universe was made of tiny, unbreakable bits moving around in an endless void. But Aristotle thought that nothingness wasn't real emptiness. It was just when something lacked a specific quality or shape, not when it had no existence at all. In ancient times, the idea that something could come out of true nothingness was very hard to accept. Instead, most believed that creation meant reshaping materials that had always been there, or that everything came out from a divine or eternal source. Then, in the early 18th century, the German thinker Gottfried Wilhelm Leibniz asked a powerful question. Why is there something rather than nothing? This simple but deep question lies at the center of all thinking about existence. If nothingness is the most basic, natural state, then why does anything exist at all? Why are we in a universe filled with stars, planets, energy, and time? Some thinkers believe this question can't be answered by science alone. It's also about purpose and meaning. In fact, certain ways of thinking, like existentialism, see nothing not as physical emptiness but as the lack of built-in meaning in the universe. If the universe has no fixed purpose, then it's up to humans to create meaning for themselves. But when we move from thinking into science, the idea of nothing takes on a very different form. For a long time, scientists also believed that empty space was simply a background, an empty stage where the events of the universe happened. That view started to change in the 17th century. Around the year 1643, Italian scientist Evangelista Torricelli made a discovery that helped prove the existence of a vacuum. He showed that when mercury is poured into a sealed glass tube and turned upside down, it leaves a space above the mercury with no air, a real vacuum. This simple device, called a barometer, led to more experiments by people like Blaise Pascal and Robert Boyle. Their work challenged Aristotle's belief that all space had to be filled, and helped scientists see that empty space was real and could be studied. Even so, many still found the idea of a truly empty void uncomfortable. In the 19th century, physicists came up with the idea of the luminiferous ether, a mysterious unseen substance they believed filled all of space and allowed light waves to move through it. But this idea fell apart in the early 20th century, when Albert Einstein's theory of relativity showed that light didn't need a medium like the ether to travel through space. Then came one of the biggest scientific changes of all, quantum mechanics. In the early 20th century, Scientists discovered that what we once thought of as empty space wasn't empty at all. Even when you remove all particles from a region of space, that space still isn't truly a nothing. Because of the Heisenberg uncertainty principle, we now know that certain properties, like energy and time, can never both be perfectly known at the same moment. This means that even in what looks like total emptiness, there's still a flicker of activity. Space is filled with tiny, short-lived particles that seem to appear and disappear quickly. These virtual particles may be unseen, but they leave behind effects that scientists can measure. One of the best examples of this is called the Casimir effect. In the year 1948, Dutch physicist Hendrik Casimir predicted something strange. If you place two uncharged metal plates very close together in a vacuum, they will slowly move toward each other, even though nothing seems to be pulling them. This happens because fewer virtual particles can exist in the small gap between the plates than in the space outside them. That creates an imbalance in pressure, which gently pushes the plates together. Later experiments proved that Casimir was right. The force between the plates shows that the quantum vacuum, the so-called empty space, is full of energy. Scientists call this unseen energy zero-point energy, and it's the lowest possible energy level that a quantum field can have, even when the temperature is absolute zero. In today's science, especially in quantum field theory, every basic particle is seen not as a tiny ball, but as a ripple in a larger field that fills all of space. There's an electron field, a photon field, a quark field, and many others. What we call empty space is really just these fields in their quietest state, without any ripples or excitations. But even in this quiet state, the fields are still there, humming softly with energy. One of the most well-known fields is the Higgs field, which gives particles their mass. Even when the Higgs field is still, it still has a non-zero value, meaning that mass can exist only because the vacuum isn't truly empty. So in science, nothing is not the same as in thinking. The scientific version of nothing is actually something. It's a restless sea of unseen fields and energy. Now, let's return to the biggest question of all. What came before the Big Bang? The standard model of cosmology says that the universe began from an incredibly hot and dense point known as a singularity. At that moment, all matter, all energy, even space and time itself came into existence. This means there was no before in the usual sense, because time didn't exist yet. If time started at the Big Bang, then asking what happened before is like asking what's north of the North Pole. It simply doesn't work in the usual way. Still, scientists have come up with ideas to go even deeper. Some modern theories suggest that the Big Bang wasn't truly the beginning. Maybe it was a kind of change, a bounce from an earlier universe or a shift from another state of reality. In repeating models, for instance, the universe goes through endless cycles of expansion and collapse. In this view, what we call nothing before our universe might have been the squeezed remains of a previous one, or a pause between two cosmic phases. So even if the current universe had a beginning, it might not have been the first universe to ever exist. One of the strongest and most interesting ideas about how the universe began comes from a theory called inflationary cosmology. This idea says that the universe did not begin by slowly growing bigger. Instead, it started with a sudden and unbelievably fast burst of expansion that happened during the very first moments of time, so early that it was only a tiny fraction of 1 second after the universe first appeared. This sudden growth was powered by something scientists call the inflaton field, a strange kind of energy field that made space stretch faster than the speed of light. In some versions of this idea, the Big Bang might not have been the very beginning of everything. Instead, it may have been caused by a tiny strange event called a quantum fluctuation. This means a sudden random change of energy that happened inside what scientists call a quantum vacuum or a false vacuum. This place was not ordinary empty space. It was a strange high-energy state filled with hidden potential. At some moment, this vacuum suddenly broke down and released an enormous amount of energy. That huge release of energy created all the matter and all the light that fill the universe today. In this way of thinking, the word nothing does not mean a complete absence of everything. It means something different, an unstable and energetic quantum vacuum, a kind of invisible mixture full of hidden activity and possibility. This nothing might even be part of something much bigger, something scientists call a meta-vacuum. A meta-vacuum could produce many universes, not just one. This idea is part of what we call the multiverse hypothesis. In this larger picture, our universe might be only one bubble floating inside a vast cosmic space that keeps creating new universes through bursts of energy. Instead of picturing nothing as a silent, empty void, some scientists describe it as quantum foam, a restless and constantly shifting foundation of reality, filled with tiny flickers of energy. This foam could be the real background from which our universe opened up, not a lifeless emptiness, but a creative and active environment where new worlds can appear. To understand this mysterious nothing, scientists are trying to answer a much deeper question. How can we bring together the two most successful theories in physics? On one side is Einstein's general relativity, which describes how gravity works and how stars, galaxies, and black holes move. On the other side is quantum mechanics, the theory that explains atoms, particles, and the tiniest pieces of matter. Joining these two into a single idea is the goal of quantum gravity, a theory that might finally explain what truly happened before the Big Bang. One promising idea is called loop quantum gravity. This theory says that space and time are not smooth or continuous the way a piece of cloth looks. Instead, they are made of tiny, indivisible building blocks like loops or grains. In this model, the universe did not shrink into a point of infinite density at the Big Bang. Rather, it became as small as it possibly could, and then it bounced outward again, starting its expansion. Scientists call this event a quantum bounce. If this idea is correct, then there was never a true singularity, and there was never a moment of complete nothing. There was only a strange state of compressed space that existed before expansion began. Another powerful idea comes from string theory, which tries to describe everything in the universe using extremely small vibrating strings instead of point-like particles. String theory also suggests that there are more than the 3 dimensions of space that we see. There may be 9 or even more dimensions, curled up so tightly that we do not notice them. In some versions of string theory, our universe may have begun when 2 giant higher dimensional surfaces called branes crashed into each other. These branes float inside a larger invisible space called the bulk. Before our universe started, there may have been an entirely different reality existing inside this bulk, a place filled with movement, energy, and possibility. In this picture, the nothing that existed before the Big Bang may have been this higher dimensional brane world, or possibly the bulk space itself. It is not a cold and empty nothingness. It is a wild, energetic, and active realm that might not include space and time the way we understand them, but which has the power to create them. All these ideas show that the scientific meaning of nothing is far more complex than it appears at first. Instead of being a perfect emptiness, it seems more like an active, energetic, and constantly changing background, something with patterns, rules, and the seeds of creation hidden inside it. Whether it is a quantum vacuum full of tiny bursts of energy, a shrunken universe preparing to bounce outward again, a floating brane ready to collide, or a network of tiny strings and loops, the nothing described by modern science always contains structure and potential. This is where science and philosophy begin to take different paths. In philosophy, the word nothing usually means a complete and total lack of anything. No space, no time, no rules, not even the possibility for something to exist. But in science, when researchers talk about nothing, they almost always mean something else. A scientific vacuum, a state where energy is low, but fields and laws still exist underneath everything. In such a vacuum, space and time may not yet have taken their familiar form, but there is still activity happening at a deeper level. The big question, can something come from true absolute nothingness, is still unanswered. Science cannot answer it, because science can only explore things that can be measured and tested. True nothingness, if it exists at all, might be unreachable, forever beyond our tools and our experiments. Even so, the search to understand this mysterious nothing continues to excite scientists, philosophers, and dreamers everywhere. The deeper we explore the universe, the more we discover that places once thought empty are actually bursting with mystery, movement, and possibility. Understanding what, if anything, existed before the Big Bang might depend entirely on how we choose to define that endlessly puzzling idea we call nothing. The Big Bang Theory is currently the most widely accepted explanation for how our universe began and how it has changed over time. It tells the story of how the universe started out in an unimaginably hot, thick state, so small it could barely be called space, and then began spreading out. Over billions of years, this spreading cooled the universe, allowing it to form the stars, galaxies, and complicated structures we see today. But it's important to clear up a common misunderstanding. The Big Bang was not an explosion in space. It wasn't like a firecracker going off in the middle of a dark, empty room. Instead, it was the stretching of space itself. Every point in the universe pulled away from every other point. Matter and energy didn't move through space. They were carried along as space itself grew bigger. This idea is central to the Big Bang theory and helps us understand that the universe has a history. It has been changing greatly since it began. The growth of this theory didn't happen overnight. It was built step by step over many years, based on careful observations and bold ideas. One of the earliest and most important thinkers was Georges Lemaitre, a Belgian priest and scientist who, in the 1920s, suggested that the universe had started from what he called a primeval atom, a single, extremely thick point of matter and energy that spread outward. This idea laid the base for what would become the Big Bang theory. Strangely, the name Big Bang wasn't meant to be taken seriously at first. It was actually made in a mocking tone by Fred Hoyle, an English astronomer who believed in a completely different idea known as the steady-state theory. He used the term to make fun of Lemaitre's idea of a beginning to the universe, but the name stayed, and oddly, became the official word for the theory he opposed. A major step forward came in the late 1920s when American astronomer Edwin Hubble made a surprising discovery. He found that faraway galaxies were moving away from Earth, and the farther away a galaxy was, the faster it seemed to be moving. This became known as Hubble's law. The light from these galaxies was stretched toward the red end of the spectrum, a change called redshift, similar to how a siren sounds lower as an ambulance drives away. This redshift showed that space itself was spreading out, pulling galaxies apart. Hubble's work offered the first direct observational proof that the universe was growing, just as Lemaitre had said. During the middle of the 20th century, there was a heated argument between two major ideas, the Big Bang theory and the steady-state theory. The steady-state model claimed that the universe had no beginning or end. It said that although the universe was spreading out, new matter was constantly being made to fill in the gaps, so it always looked the same overall. For a while, both theories had their supporters. But then, two huge discoveries changed everything. In the year 1964, scientists Arno Penzias and Robert Wilson were using a large horn-shaped antenna when they picked up a strange steady hiss, like static from all directions in the sky. At first, they thought it was just noise from the equipment, or even pigeon droppings in the antenna. But it turned out to be something far more important, the cosmic microwave background, or cosmic microwave background. This faint glow is the leftover radiation from the very early universe. According to the Big Bang theory, the universe once looked like a hot, thick fog of particles and radiation. As it spread and cooled, it eventually became clear enough for light to travel freely. That ancient light is what we now detect as the cosmic microwave background. It is like a frozen picture of the universe when it was just 380,000 years old, a baby in cosmic terms. Its smooth temperature pattern across the sky matches exactly what the Big Bang theory predicts. This discovery became one of the strongest pieces of proof for the theory. The second major discovery came from studying the amounts of light elements in the universe, things like hydrogen, helium, and tiny traces of lithium. The Big Bang theory predicts that during the universe's first few minutes, it was hot enough for nuclear fusion, the same process that powers the sun, to happen. In this short time, particles joined together to create the centers of these light elements in a process called Big Bang nucleosynthesis. And here's the amazing part. When scientists measured the actual amounts of these elements in the universe, they matched the predictions of the Big Bang model almost perfectly. About 75% of the visible matter in the universe is hydrogen, and about 25% is helium, just as expected. This exact match was a huge proof that the Big Bang really happened. Together, these three pillars, the spreading universe, the cosmic microwave background, and the amount of light elements, form a solid base for the Big Bang theory. The true beginning of the universe is still covered in mystery. Scientists believe everything began at a moment known as the Planck epoch, which was just 1 10 million trillion trillionth of a second after time itself started. about 10 to the power of minus 43 seconds. During this tiny bit of time, the universe was so hot and thick that the four basic forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were all combined into a single force. But our current physics breaks down here. We simply don't have a complete theory to describe what exactly happened at that moment. Right after the Planck epoch, something amazing is thought to have happened, a burst of incredibly fast spreading known as inflation. This idea was suggested in the early 1980s, mainly by scientist Alan Guth, to solve several problems in the original Big Bang model. One problem was the horizon problem. How could parts of the universe so far apart have the exact same temperature if light hadn't had time to travel between them? Another was the flatness problem. Why does space seem almost perfectly flat rather than curved in some way? And finally, the monopole problem. If certain strange, heavy particles should have been made in the early universe, why haven't we found any? Inflation suggests that the universe grew by a factor of at least 10 to the power of 26 in a tiny fraction of a second. That's a number so large it's hard to even imagine. This fast growth would have smoothed out the universe, flattened its shape, and thinned out any unwanted particles. It also explains the tiny ripples in the early universe, small changes in density that later grew into galaxies and clusters of galaxies. After inflation ended, the universe didn't stop spreading, but it slowed down. The energy from inflation was changed into a hot, thick mix of particles and forces called a quark-gluon plasma. It was so hot that even the building blocks of protons and neutrons, tiny particles called quarks, couldn't stick together yet. But as the universe spread, it cooled. Eventually, the strong nuclear force became strong enough to bind quarks into protons and neutrons. This time is known as the Hadron Epoch. During this time, there was a tiny imbalance. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. As the universe cooled further, matter and antimatter crashed into each other and destroyed each other. But that little extra bit of matter survived, and that's what makes up everything we see today, from stars and planets to you and me. A few minutes after the Big Bang, when the universe had cooled to about 1 billion degrees Celsius, conditions were just right for nuclear fusion. Protons and neutrons joined together to form the centers of the first elements: deuterium, a form of hydrogen, helium-3, helium-4, and tiny amounts of lithium-7. These reactions lasted for only about 20 minutes, but their results are still all around us. The exact mix of these elements is one of the strongest and clearest signs that the universe really began in a hot, thick state, just as the Big Bang theory says. For the next few 100,000 years after the Big Bang, the universe was in a hot, thick, and shining state. It wasn't yet the clear space we know today. Instead, it was filled with a thick soup of ionized hydrogen and helium centers, which means the atoms were broken apart into their cores and free-floating electrons. Light particles called photons were everywhere, but they couldn't travel far. Every time they tried to move, they bounced off those free electrons, getting absorbed or scattered. The result was a universe that looked like a glowing fog, completely non-see-through, meaning light couldn't pass through it. This time in the universe's life is known as the photon epoch. During this period, light, or radiation, was the most important and powerful form of energy. It ruled over matter, shaping the behavior of the cosmos. But the universe didn't stay in that hot, foggy state forever. As space spread out, it also cooled down. Around 380,000 years after the Big Bang, the temperature finally dropped to about 3,000 Kelvin, which was just cool enough for something amazing to happen. The free electrons began to join together with hydrogen and helium centers, forming the very first stable atoms. This moment is called recombination, and it changed everything. Once atoms were formed, light was no longer constantly bumping into loose charge particles. Now, photons could finally travel freely across the universe without being stopped. Space became clear for the first time. The light from that moment is still around us today. It's incredibly faint and stretched into the microwave part of the spectrum, but we can still see it. It's called the cosmic microwave background. Cosmic microwave background. The oldest light we can see, a kind of glowing baby picture of the universe. Scientists often call it the surface of last scattering, because it marks the last time photons scattered before moving freely into space. It gives us a direct view of what the early universe looked like just after it became clear. But after this glowing moment, a deep silence followed. the universe entered a long, dark time called the Cosmic Dark Ages. For hundreds of millions of years, there were no stars, no galaxies, and no new light. Space was filled with nothing but cold, neutral hydrogen and helium gas, and the faint background glow of the cosmic microwave background. It was a time of stillness, with only one major force at work: gravity. Tiny differences in the thickness of matter, left behind from an earlier time of fast cosmic inflation, began to pull things together slowly. Thicker areas pulled in more gas and dark matter. Over huge stretches of time, these small ripples grew into giant clouds. Some of these clouds eventually collapsed under their own gravity, starting the first stars and quasars, brilliant lights that brightened the cosmos. These first lights were incredibly strong. They began to break apart the neutral hydrogen gas that had filled the universe for so long, turning it back into charged particles. This process, called reionization, filled the universe with ultraviolet radiation and marked the end of the Dark Ages. This new era, the epoch of reionization, began somewhere between 150 million and 1 billion years after the Big Bang. As time passed, gravity continued to do its work, slowly but surely building up more and more structure. The slightly thicker areas of gas and dark matter kept pulling in more material. Eventually, these growing clumps formed the first galaxies, huge collections of stars, gas, and dust. Galaxies grouped together into galaxy clusters, and those clusters joined to form even bigger superclusters. Over time, all of this structure formed a vast network known as the cosmic web, a beautiful, huge pattern of strands and empty spaces where galaxies are arranged in long threads separated by enormous blank areas. None of this would have been possible without dark matter, a strange, invisible kind of matter that doesn't give off light or interact with ordinary atoms, but has gravity. Dark matter acts like the support beams of the universe, helping regular matter gather and form stars and galaxies. Without it, the large-scale structures we see today would never have formed. Then, in the last few billion years, something surprising happened. Astronomers studying faraway exploding stars, called supernovae, in the late 1990s made a shocking discovery. The universe's spreading wasn't slowing down like everyone expected. It was actually speeding up. Something was pushing everything apart. This strange force is now known as dark energy. Unlike dark matter, which helps bring things together, dark energy acts like an opposite gravity force, making the fabric of space stretch faster and faster. No one knows exactly what dark energy is. It might be a basic feature of space itself, or it could be something entirely new, some strange energy field we don't yet understand. But today, dark energy makes up most of the energy in the entire universe. Its effects are so strong that they now control the universe's behavior. If dark energy keeps acting the way it does now, or becomes even stronger, the universe will continue to spread faster and faster. In the far future, galaxies will drift so far apart that they'll no longer be able to see each other. Stars will eventually burn out, and the universe could become a cold, dark, lonely place. Even though the Big Bang Theory is incredibly successful at explaining the history of the cosmos, it still doesn't answer everything. In fact, it leaves us with some of the biggest questions of all. The most puzzling mystery is this: what happened before the Big Bang? The theory explains how the universe grew from a very hot and thick beginning, but it doesn't tell us what started that beginning, or if anything existed before it. The idea of a singularity at the very start, a point where our current understanding of physics completely breaks down, is still one of the biggest challenges in cosmology. And then there's dark matter and dark energy. Together, they make up almost 95% of the universe, yet we still don't know what they're made of. We can see their effects, but we don't understand their true nature. Even the process of cosmic inflation, a fast burst of spreading that likely happened just before the Big Bang as we know it, remains mysterious. It helps solve many problems in cosmology, but scientists are still working hard to understand what caused it, what kind of field or particle was responsible, and how it shifted into the hot plasma that started the Big Bang itself. The story of how our universe changed and grew is like an ancient tale written in the language of atoms and light. It began with a hot, dense mix of tiny particles, protons, neutrons, electrons, and photons, all swirling together in an incredibly energetic state. From this fiery chaos, something amazing happened. the birth of the very first atomic nuclei. This event is known as Big Bang nucleosynthesis for short, and it took place just a few short minutes after the universe itself came into existence. This moment in cosmic history is extremely important. Why? Because it explains why we see the lightest elements, hydrogen, helium, and lithium, scattered all across the cosmos in just the right amounts. These elements were not made in stars like heavier ones were. Instead, they were created quickly and smoothly in the first glowing moments of the universe's life, under very special and extreme conditions. For this early process of nucleosynthesis to begin, the universe had to be in just the right state. It needed to be hot enough for particles to crash into one another and fuse, just like in the core of a star, but also cool enough so that the new atomic nuclei didn't get instantly torn apart by energetic light particles known as photons. This delicate balance was achieved when the universe was about 3 minutes old, and it lasted for only 17 minutes, until the universe was roughly 20 minutes old. During that brief and important window, the temperature dropped to about 1 billion degrees Celsius. That's still unimaginably hot, but compared to earlier moments, it was just cool enough to allow nuclear building blocks to stay together. The density of the universe also mattered a lot. It had to be high enough so that protons and neutrons could collide often and form nuclei, but not so high that all the neutrons were immediately used up in reactions. Luckily, the steady expansion and cooling of the universe helped create and then shut down this window of chance at just the right time. At the start of Big Bang nucleosynthesis, the universe was mostly made up of free protons and neutrons, surrounded by a sea of electrons and photons. A proton is basically the nucleus of a hydrogen atom, the simplest and lightest of all elements. A neutron is slightly heavier and is not stable on its own. When left alone, a neutron will naturally break down into a proton, an electron, and a tiny particle called an antineutrino. This breakdown happens with a half-life of about 10 minutes. Before nucleosynthesis began, there was a constant back and forth happening between protons and neutrons. Thanks to the weak nuclear force, protons could turn into neutrons and vice versa. These reactions kept the number of each type balanced. But as the universe expanded and cooled, the weak force lost its grip. By the time the universe was just 1 second old, the temperature had dropped to about 10 billion degrees Celsius, and these proton-neutron changes slowed down a lot. Because neutrons are heavier and naturally break down, there ended up being fewer of them. For every 1 neutron, there were about 6 or 7 protons. This 1:7 ratio was incredibly important. It would go on to decide how much helium could form. If there had been more neutrons, more helium would have been made. If there had been fewer, less helium would exist today. This fine balance helped shape the chemistry of the entire universe. But even with the right number of protons and neutrons, building atomic nuclei wasn't easy. The very first step was creating deuterium, which is a special kind of hydrogen with 1 proton and 1 neutron. Deuterium is fragile, like trying to stack cards during a windstorm. In those first minutes, the universe was still so hot that any deuterium formed would be instantly broken by photons. Scientists call this problem the deuterium bottleneck. It wasn't until the universe cooled down to around 1 billion degrees Celsius, about 3 minutes after the Big Bang, that deuterium nuclei finally became steady enough to survive. Once this happened, everything changed. Like floodgates bursting open, nuclear fusion began for real. Deuterium started to join with protons to form helium-3, or with other deuterium to create either helium-3 plus a neutron, or tritium, another hydrogen type with 1 proton and 2 neutrons. These lighter nuclei quickly fused to form helium-4, a very steady form of helium made of 2 protons and 2 neutrons. Because helium-4 is so steady, and the fusion reactions were so strong, nearly every neutron that had survived breakdown got locked into a helium-4 nucleus. This led to an amazing outcome. By the time Big Bang nucleosynthesis ended, the universe had a first mix of about 75% hydrogen and 25% helium by mass. This surprising prediction, based purely on early universe physics, matches almost perfectly with what astronomers see today. But the story doesn't end there. Although hydrogen and helium were the main products, a tiny amount of other light elements were also made, most notably lithium-7. This came from rare fusion reactions, such as helium-4 fusing with tritium, or from the breakdown of beryllium-7 into lithium-7. However, the universe wasn't able to make much lithium, and it certainly couldn't make anything heavier. Why not? Because there are no steady atomic nuclei with 5 or 8 particles inside. This creates a kind of mass gap in nuclear fusion. So even if a helium-4 nucleus tried to fuse with a proton or a neutron, the result would be shaky and fall apart. To go beyond this limit, to build elements like carbon, oxygen and iron, requires a much calmer, more steady environment with high pressure and heat lasting millions or billions of years. That environment is found inside stars, not in the fast-cooling universe of the Big Bang. So, in just under 20 minutes, the universe wrote the opening chapter of the periodic table. It created nearly all of the hydrogen and helium we see today, along with tiny sprinkles of lithium. The rest, the gold in our jewellery, the oxygen we breathe, the calcium in our bones, would come much later, from the hearts of stars and the explosions of dying suns. The predictions made by Big Bang nucleosynthesis, the process that created the universe's first light elements, are not just ideas written down in theory books. They have stood up strongly to the test of real-world observation. In fact, scientists have found that the actual amounts of these early elements seen across the cosmos match the predictions extremely well. To check how much of these light elements were made in the early universe, astronomers try to study areas of space that have stayed mostly untouched since the beginning. These are places that haven't been heavily changed or polluted by newer elements made later in stars. The best environments for such studies are ancient dwarf galaxies or faraway clouds of gas that contain almost no heavy elements, meaning they're as close as we can get to the original makeup of the universe. For example, astronomers measure the amount of deuterium, a heavier version of hydrogen, by studying the light from extremely distant quasars. As this light travels through clouds of ancient gas on its way to Earth, it leaves behind special signs called absorption lines. These lines show how much deuterium is in those clouds. To find out how much helium-4 was created, scientists look at blue compact dwarf galaxies. These are small galaxies where very few stars have formed, so their gas has hardly been changed. They're perfect for measuring how much helium-4 came straight from the Big Bang. As for lithium-7, its tiny traces are found in the outer layers of some of the oldest stars in the Milky Way's outer halo. These stars are thought to have formed from gas that was almost completely untouched since the universe's earliest days. What's truly amazing is that the seen amounts of hydrogen, deuterium, helium-3, helium-4 and lithium-7 all line up beautifully with the exact amounts predicted by Big Bang nucleosynthesis. This match is one of the strongest pieces of proof we have that supports the idea of a hot, dense beginning for our universe, what we call the Big Bang. But the success of Big Bang nucleosynthesis doesn't end there. It also helps scientists figure out some of the universe's most important numbers, its basic physical properties. One example is the density of ordinary matter, which scientists call baryonic matter. The predicted amounts of the light elements depend on how much of this matter was present in the early universe. So by comparing the actual seen amounts of these elements with the predictions, scientists can work out how much ordinary matter there is in the cosmos. And what's surprising is that this number matches perfectly with results from a completely different method. Studies of the cosmic microwave background, the faint glow left behind from the early universe. This match between two totally separate lines of proof gives scientists great confidence that they're on the right path in understanding the basic structure of the universe. Big Bang nucleosynthesis also gave early hints about how many types of light neutrinos, ghostly, nearly weightless particles, exist in nature. Long before lab experiments could confirm it, BBN calculations strongly pointed to there being exactly 3 types of light neutrinos. Later, particle physics experiments backed this up, proving just how powerful BBN theory really is. However, not everything is perfectly understood. One mystery remains, and it's known as the lithium problem. When scientists measure the amount of lithium-7 in those ancient stars, they always find less than expected, only about 1/2 to 1/3 of the predicted amount. This difference is puzzling and still not fully explained. There are a few possible reasons for this lithium difference. It could be that our models of how stars work, especially how their outer layers affect lithium, are not quite right. Another idea is that something new and unknown in physics might be changing the way lithium was created or destroyed in the early universe. Or maybe there are hidden mistakes in how we understand the nuclear reactions that made lithium in the first place. Whatever the cause, this problem remains an active area of study. Even with this one unsolved issue, the overall match between the predictions of Big Bang nucleosynthesis and the seen amounts of hydrogen and helium is so strong that BBN remains one of the key supports of modern cosmology. The bare nuclei formed during this process, mostly hydrogen and helium, became the raw material for nearly all the visible matter in the universe. These hot charged particles stayed in a plasma state until the universe had cooled enough for electrons to join them, forming neutral atoms. That moment marked the beginning of the cosmic dark ages, a time before stars and galaxies had formed, and set the stage for everything that followed in the universe's grand story. The timeline of the universe explains its history and future according to the idea of the Big Bang. The very first moments after the Big Bang, called the Planck epoch, happened in the first trillionth of a second, a picosecond. During this time, the usual laws of physics might not have worked. This period also saw the slow appearance of the four basic forces we know today: gravity first, then electromagnetic forces, weak forces, and strong forces. The universe expanded very fast in a process called cosmic inflation. Tiny changes, or ripples, in the universe during this early time are thought to have played a key role in forming the large structures we see today, like galaxies. While we understand some of the early universe's stages, we still don't have the tools to directly test them in particle physics experiments. However, by using known physical laws at extremely high temperatures, we can still make educated guesses about what happened. For about 380,000 years after the Big Bang, the universe went through big changes. At first, a mix of tiny particles formed in steps. There was almost the same amount of matter and antimatter, but most of it destroyed itself in an explosion of energy, leaving a small amount of matter behind, which became the building blocks of everything we know. Around 1 second after the Big Bang, neutrinos, tiny particles that barely interact with anything, separated from other particles, creating what we now call the cosmic neutrino background. If primordial black holes existed, they would have formed around this time too. Around 2 minutes later, protons and neutrons joined together to make more complex tiny particles. By the time 2 minutes passed, conditions were right for nuclear fusion, letting the first elements form. About 25% of the protons and all the neutrons fused into heavier elements, starting with deuterium, which quickly became helium-4. By 20 minutes after the Big Bang, the universe was no longer hot enough for nuclear fusion to continue, but still too hot for atoms to form or light to travel freely. At this point, the universe became a dense, cloudy plasma. Around 18,000 years after the Big Bang, electrons began joining with helium nuclei, starting the recombination epoch. By 47,000 years, as the universe cooled, matter began to take over from radiation. By 100,000 years after the neutral helium atoms formed, helium hydride was the first molecule to appear. Later, hydrogen and helium hydride joined to form molecular hydrogen, which would become the fuel for the first stars. Around 370,000 years after the Big Bang, neutral hydrogen atoms fully formed during what is called recombination, which made it possible for photons, light, to travel freely. These photons were no longer scattered by free electrons and instead moved through the universe without interruption. These ancient photons are still detectable today as the cosmic microwave background, CMB, the oldest light we can see. From about 380,000 years to around 1 billion years after the Big Bang, matter began to clump together around pockets of dark matter. Slowly, clouds of hydrogen collapsed to form the first stars and galaxies. This period, called the Cosmic Dark Ages, was a time when there were very few sources of light. Most of the photons that existed were the ones released during the decoupling process, which we still detect today as the cosmic microwave background, or 21 centimeters radio signals from hydrogen atoms. Light was rare, and the universe stayed mostly dark until the first stars began to shine. Between 200 million to 500 million years after the Big Bang, the first stars and galaxies began to form, though scientists are still working to find the exact time. As the universe expanded, large structures slowly took shape, pulled together by dark matter filaments that acted like invisible webs, drawing matter into clumps. These early stars, which haven't been seen directly yet, were probably huge, some weighing 100 to 300 times more than our Sun, and made mostly of hydrogen and helium, with little to no metals. Because they were so big, they used up their fuel quickly, living only a few million years before exploding in a powerful event called a pair instability supernova. Other ideas suggest that some of these early stars could have been smaller, and maybe a few of them are still shining today. These supernovae created the basic elements we see around us, like carbon and oxygen, and spread them through the universe, adding the building blocks of life. Over time, galaxy clusters and superclusters began to form. Around 250 to 500 million years after the Big Bang, high-energy radiation from the first stars, small galaxies, and even quasars caused a process known as reionization. This event slowly happened over a period that lasted until about 1 billion years after the Big Bang, though the exact timing is still being studied. It marked the end of the dark ages of the universe, a time when everything was still very dense and quiet. By 1 billion years, the universe was starting to look more like it does today, but it was much hotter, more active, full of smaller galaxies and intense star formation. At this point, galaxies started to change from being giant elliptical ones to smaller, unbarred spirals and irregular shapes. The earliest galaxies that scientists have seen date back to about 330 million years after the Big Bang, roughly 13.4 billion years ago. These galaxies were very young and had few elements heavier than hydrogen, making them metal-poor. Spectroscopic evidence shows that they were surrounded by a cloud of neutral hydrogen, just as scientists expected. Studies also suggest that these galaxies formed quickly in a place full of strong radiation. From around 1 billion years after the Big Bang, the universe began to look much like it does today, and it has stayed in this state for the last 12.8 billion years. This period is expected to last for many billions of years to come. The Milky Way, for example, started forming its thin disk when the universe was about 5 billion years old, and our solar system formed about 9.2 billion years after the Big Bang. Life on Earth, however, began much later, about 10 billion years after the Big Bang. As the universe got older, matter began to thin out, which slowed its ability to pull the universe back together with gravity. At the same time, dark energy, an invisible force, started to take over, causing the expansion of the universe to speed up. This change happened about 5 or 6 billion years ago, marking the start of the dark energy-dominated era, where the universe's expansion is getting faster instead of slower. While we have a good understanding of how the universe works today, we aren't sure what will happen in the far future, after around 100 billion years, or about 86 billion years from now. At some point in the far future, the stelliferous era will end. This will happen when stars stop being born, and as the universe keeps expanding, we will only be able to see galaxies that are close to us. The ultimate fate of the universe is still unknown, with many possible outcomes to consider. As we learn more about the universe today, we might better understand what will happen next. The expansion of the universe that we see today led to the creation of the Big Bang theory. This theory says that the universe started from a state of extremely high temperature and density. A more detailed version of this theory, called the lambda CDM model, matches a wide range of space observations. However, when we trace this expansion back to even higher temperatures and densities, we reach a point where current physical models cannot make accurate predictions or stop working entirely. As we reach infinite temperature or a scale factor of 0, basically the moment the universe began, our physical models no longer work. At this stage, thinking about an initial gravitational singularity doesn't make sense, because it is beyond our current understanding of physics. The standard model of cosmology tells us that the universe has been growing since it was very hot, but as we try to follow this growth backward, we reach a point called the Planck length. Below this distance, the physics laws we rely on don't work anymore, and the energy in the particles becomes so extreme that quantum effects take over, replacing Einstein's gravity equations. The Planck time, which is extremely short, marks the start of the Big Bang according to cosmology models. After the Planck era, the universe could, in theory, be described by extensions of the standard model of particle physics, like grand unified theories, GUTs. However, no GUT has yet been able to match modern observations. The time between a zeptosecond and a rontosecond is called the grand unification period, although this is still uncertain. Before this grand unification period, the universe was so hot that its temperature went beyond quadrillion giga-electron volts. As the universe grew and cooled, it may have gone through a phase change, similar to how gas turns into liquid or freezes into solid, which could explain the large amount of matter compared to antimatter we see today. While the grand unification phase is still uncertain, changes like the electroweak and quark-hadron phases are supported by theory, and have made successful predictions. The electroweak period, depending on the model, could have started before or after the inflation period, or in some models it could even overlap with it. In some views, it began after inflation ended, roughly Ronto seconds after the Big Bang. At this early stage in the universe's life, it is thought to have grown by an enormous amount, at least sextillion times its original size. This is like taking something as small as a nanometer, about the width of a DNA molecule, and expanding it to over 10.6 light years, which is about 100 trillion kilometers, in just a tiny fraction of a second. This rapid growth is called cosmic inflation, and it marks an important period in the universe's development. The exact cause of inflation, the rapid growth of the universe, is still not fully known, even though many ideas have been suggested. One popular idea says inflation started when two main forces, the strong and electroweak forces, split apart, ending the grand unification period. During this time, a special field called the inflaton field was created. As this field spread through the universe and settled into its lowest energy state, it made a huge repulsive force that caused the universe to grow very quickly. Inflation helps explain several strange features of the universe today that would otherwise be hard to understand. For example, it explains how the universe, which began as a smooth and evenly spread space, now has galaxies and galaxy clusters. The small random differences in the universe's early state, which were made bigger during inflation, eventually formed the large structures we see now. We don't know exactly when inflation ended, but it is thought to have stopped between 10 to 33 and 10 to 32 seconds after the Big Bang. The universe grew so quickly that leftover particles from the grand unification period were spread out over huge distances. Then, at the end of inflation, the inflaton field released its energy, a process called reheating. This release created a hot and dense mix of particles like quarks, antiquarks, and gluons. Some ideas suggest that this reheating phase started the electroweak period, while other models, like warm inflation, don't have a separate reheating phase at all. After inflation, the universe kept growing, but much more slowly. Around 4 billion years ago, the growth began to speed up again, likely because dark energy started controlling the universe's behavior. This faster expansion is still happening today. After inflation, the universe was full of a superheated plasma made of quarks and gluons left over from reheating. After this stage, scientists have a much clearer idea of what happened in the early universe because the conditions of the quark period can now be recreated in particle physics experiments. As time went on, the particles created during inflation went through a process called thermalization, where they interacted and reached a balanced energy state. Before a major change called electroweak symmetry breaking, which happened about 10 to 15 seconds after the Big Bang at temperatures around 1015 K, the electromagnetic and weak forces had not yet split apart. The particles hadn't gained mass through the Higgs mechanism yet. This phase ended when electroweak symmetry breaking happened, possibly as part of a phase change. Some versions of the standard model say that during this time, baryogenesis happened, causing a small imbalance between matter and antimatter, though some theories say this imbalance might have happened even earlier. The details are still unknown. As the universe's temperature continued to drop below 159.5 plus or minus 1.5 gigaelectron volts, an important event called electroweak symmetry breaking happened. This event, after the universe's early growth, was the second to last major change in the universe's structure, with the last being chiral symmetry breaking in quarks. This change had two main effects. First, through the Higgs mechanism, all the tiny particles in the universe started to gain mass. Before this, they had no mass, but as the temperature dropped and energy went down, these particles started interacting with the Higgs field and became massive. Second, the weak nuclear force and electromagnetic force began to act differently. These forces, along with their particles, the W and Z bosons, which carry the weak force, and the photon, which carries the electromagnetic force, went through a big change. Before electroweak symmetry breaking, all these forces and particles had no mass and could act over long distances. But after symmetry breaking, the W and Z bosons became heavy and could only act over distances smaller than an atom, while the photon stayed massless and could still act over long distances. After this key event, the four main forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were set in the forms we know today. The basic particles also had their expected masses, but the universe was still too hot for many particles to form stable structures. So there were no protons or neutrons yet, and no atoms, atomic nuclei or molecules. Any particles that did form briefly would break apart almost immediately due to the extreme energy. This period, called the quark period, began roughly 10 to 12 seconds after the Big Bang. It was just after electroweak symmetry breaking, when the universe's main forces had taken their current forms, but the temperature was still too high for quarks to combine into bigger particles. During this period, the universe was a boiling mix of quarks, gluons, leptons and their opposites, all in a hot, dense plasma. The energy from constant collisions was so high that quarks couldn't combine to form mesons or baryons. The quark epoch ended when the universe was about 10 to 5 seconds old. At this point, the temperature dropped enough for the energy from particle interactions to fall below the mass of the lightest particle made from quarks, the pion. Baryons, like protons and neutrons, are made up of 3 quarks, and it was expected that for every baryon made, an equal number of antibaryons would form as well. However, this didn't seem to happen. The universe ended up with far more baryons than antibaryons, and in fact, very few antibaryons are seen in the universe today. Scientists are still not sure how this imbalance happened. Any explanation must meet certain conditions connected to baryogenesis, which happened after the universe's rapid inflation. While some ideas exist that might explain this imbalance, the differences involved seem too small to fully account for the huge difference between baryons and antibaryons that we see. The theory says that for every 6 protons there was about 1 neutron, though this ratio later dropped to 1 neutron for every 7 protons because neutrons decay over time. This idea is supported by evidence that later on neutrons and some protons joined together to form elements like hydrogen, a hydrogen isotope called deuterium, helium, and other elements, which we can still measure today. The 1:7 ratio of hadrons would lead to the same proportions of elements we see in the early and current universe. About 1 second after the Big Bang, neutrinos, tiny particles that hardly interact with matter, separated from the hot, dense matter and started moving freely through space. These neutrinos, which are still around today, are similar to the cosmic microwave background, CMB radiation we see today, which was released much later, around 370,000 years after the Big Bang. The neutrinos from that early time have very low energy. Detecting high-energy neutrinos is already hard, so this background of cosmic neutrinos, CNB, may stay invisible for many years, or maybe forever. However, Big Bang cosmology predicts a lot about the CNB, and there's strong indirect evidence for it. This evidence comes from predictions about how much helium was made during Big Bang nucleosynthesis, and from uneven patterns seen in the CMB. One prediction is that neutrinos would have left a tiny mark on the CMB. We already know the CMB shows some uneven patterns. Some of these patterns happen at regular intervals because of a process called baryonic acoustic oscillations. According to the theory, the neutrinos that separated early should have caused tiny shifts in the phases of these patterns. In 2015, scientists announced that they had found these shifts in the CMB. The patterns they found matched the temperature of neutrinos predicted by the Big Bang theory. Also, they detected exactly 3 types of neutrinos, matching the 3 flavors expected according to the standard model of particle physics. Primordial black holes are a hypothetical type of black hole suggested in 1966, which could have formed during the radiation-dominated era of the universe if the universe had enough irregularities. Small differences in density might have caused some areas to collapse under their own gravity, forming black holes. Meanwhile, most hadrons, like protons and neutrons, and antihadrons, their opposites, would have destroyed each other, leaving behind leptons, like electrons, muons and neutrinos, and antileptons. In the early universe, leptons and antileptons appeared in pairs. About 10 seconds after the Big Bang, the universe cooled enough that new lepton-antilepton pairs stopped forming. Most of the remaining leptons and antileptons destroyed each other, turning into high-energy photons. However, a few leptons survived, leaving a small amount behind that added to the mass of the universe. After most leptons and antileptons were gone at the end of the lepton epoch, the universe's energy mostly stayed in photons. The rest was mainly in the form of neutrinos and other fast-moving particles. Because of this, photons became the main form of energy in the universe and controlled how it behaved. For the next 370,000 years, photons kept interacting regularly with charged particles like electrons, protons, and eventually atomic nuclei. Between 2 and 20 minutes after the Big Bang, nuclear fusion started. During this time, a mix of neutrons and protons, about 1 part in 7, began fusing into different elements like protons, deuterium, a proton fused with a neutron, and helium isotopes, like helium-3 and helium-4, with tiny amounts of lithium and beryllium. This process stopped when the temperature dropped below what was needed for fusion. The exact mix of elements made depends on factors like reaction rates, temperature, and particle density. Scientists can measure the reaction rates in labs, while temperature and density can be calculated using models of the universe's expansion. About 25% of protons and all neutrons combined to form deuterium, a hydrogen isotope, and most of this deuterium quickly fused into helium-4. Helium-4 has a stronger binding energy than nuclei with 5 to 8 particles, so very few of these heavier nuclei were made. Heavier elements made in stars don't form because they need 3 helium-4 nuclei to join, but the universe expanded too fast for that to happen before the temperature cooled too much. Some tritium, another hydrogen isotope, and small amounts of beryllium-7 and beryllium-8 were made but were unstable and decayed quickly. A small amount of deuterium was left behind unfused. By studying old galaxies, scientists can estimate how much of each light element was made in the early universe, which strongly supports the Big Bang theory. For example, we see that about 1 neutron was made for every 7 protons, allowing 25% of all particles to fuse into helium-4. This matches the amount we see today, which is much more than can be explained by stars alone. Deuterium, which fuses easily, also gives strong evidence for the Big Bang because any other theory would need to explain why deuterium was made and why some of it wasn't fused into helium right away. Any other theory must also explain the exact proportions of the light elements and their isotopes, with some isotopes like lithium-7 showing small differences from what theory predicts. For much of the universe's early history, its large-scale behavior was mostly controlled by radiation, particles that move near the speed of light, like photons and neutrinos. But as the universe cooled, around 47,000 years after the Big Bang, matter started to take over. This happened because the density of matter became higher than both the density of radiation and the energy from empty space. Around this time, the densities of matter, in the form of atomic nuclei, and radiation, photons, became equal. This change allowed small structures to begin forming, as gravity could now overcome the pressure from radiation, letting these structures grow instead of being wiped out by radiation. According to the lambda-CDM model, by this point, about 84.5% of the universe's matter is cold dark matter, and the rest, 15.5%, is regular matter. There's strong evidence for dark matter, which plays a major role in the universe's structure, but scientists still don't fully understand what dark matter is, so the Big Bang theory doesn't yet explain how it formed. For billions of years ahead, dark matter will keep affecting how the universe's structure develops. In the early universe, dark matter started to clump together in huge filaments because of gravity, pulling together much faster than ordinary matter. This is because dark matter doesn't interact with radiation like regular matter does. As it gathers, it increases small differences in the universe's density left behind by cosmic inflation. Over time, denser regions became even denser, while areas with fewer particles became emptier. These dark matter clumps helped ordinary matter come together faster than it would have alone. One reason dark matter clumps quickly is that it doesn't lose energy through radiation. For particles to form dense structures like stars or planets, they need to lose energy, but dark matter can't do this. Instead, it forms large, thin filaments and halos, rather than compact objects. Regular matter, however, can lose energy by giving off radiation, which lets it collapse into denser objects like stars or gas clouds. Around 370,000 years after the Big Bang, 2 major events happened: recombination and photon decoupling. Recombination is when ionized particles, like electrons and protons, join to form the first neutral atoms. Photon decoupling happens when the photons, which were trapped by interactions with these particles, were freed as the new atoms reach stable energy states. Before recombination, the universe was extremely hot, and matter was in the form of ionized plasma. The photons kept interacting with the charged particles, stopping them from moving far. Because of this, the universe was opaque, almost like a fog. There was light, but it wasn't possible to see through it with telescopes. As the universe cooled over time, starting around 18,000 years after the Big Bang, electrons began joining with helium nuclei to form helium atoms. Neutral helium started forming at about 100,000 years, and hydrogen atoms followed around 260,000 years. This is called recombination, though the name is a bit misleading because it was the first time electrons and nuclei joined. Around 100,000 years later, the universe cooled enough for the first molecule to form, helium hydride. This was an important step in the history of molecular chemistry. In April 2019, scientists confirmed that helium hydride had been seen in space, specifically in the planetary nebula NGC 7027. Later, this molecule would interact with atomic hydrogen, leading to molecular hydrogen, the main ingredient for star formation. When hydrogen atoms combine in a low-energy state, it's not very efficient. Usually they combine while still holding their high-energy electrons. After combining, these electrons quickly release energy, dropping to lower energy states and giving off photons. This release of photons is called photon decoupling. Some of these photons are caught by other hydrogen atoms, while the rest stay free. By the time recombination finishes, most protons in the universe have joined with electrons to form neutral hydrogen atoms. This change from charged particles to neutral ones changes how far photons can travel before being caught. After recombination, photons can travel freely without being blocked, making the universe see-through to light, radio waves, and other types of electromagnetic radiation for the first time. The photons released by these neutral hydrogen atoms had a temperature of about 4000 K, which would have looked like a soft white light with a pale yellow or orange tint to the human eye. Over billions of years, as the universe expanded, these photons stretched out, moving from visible light to longer wavelength radio waves, now seen as microwave radiation, with a temperature of about 2.7 K. This process, called redshifting, happens because the universe's expansion makes photon wavelengths longer and their frequencies lower. These redshifted photons can still be detected today as radio waves, forming the cosmic microwave background. This radiation gives important clues about the early universe and how it developed. Around the same time as recombination, there were pressure waves in the electron-baryon plasma, which became locked into the matter as it condensed. These pressure waves, called baryon acoustic oscillations, left a small pattern in the large-scale structure of the universe. The cosmic microwave background shows a snapshot of the universe from the end of this period, including tiny fluctuations from the early moments of inflation. The spread of galaxies today reflects the size and growth of the universe over time. After recombination and decoupling, the universe became see-through, but it was still too cool for stars or galaxies to form. Stars and galaxies only started to appear when gravity made dense regions of gas collapse, a process that took hundreds of millions of years. This long wait is why stars didn't appear until much later after recombination. This period, called the Dark Ages, started around 370,000 years after the Big Bang. During the Dark Ages, the universe cooled from about 4000 K to 60 K. Only two sources of photons existed then, the ones released during recombination, which we still see as the cosmic microwave background, CMB, and photons occasionally given off by neutral hydrogen atoms, called the 21 cm spin line. The 21 cm spin line is in the microwave frequency range. Within just 3 million years, the CMB photons had moved from visible light to infrared. For a long time after that, there was no visible light in the universe, and aside from a few rare cases, it was truly dark until the first stars formed. The first stars in the universe, called population 3 stars, began forming a few hundred million years after the Big Bang. These stars were the first to shine with visible light, ending the universe's Dark Ages, a time when no light was seen. Around 150 million years after the Big Bang, structures may have started to take shape, and by 180 to 700 million years later, early galaxies began appearing. This slow process continued, and it wasn't until about 1 billion years after the Big Bang that the Dark Ages fully ended, and the universe looked more like it does today. Currently, the oldest stars and galaxies observed are from just after the start of a process called reionization, which happened around 400 million years after the Big Bang. The Hubble Space Telescope in 2016 observed galaxies like GNZ 11, which existed about 400 million years after the Big Bang. The James Webb Space Telescope, launched in December 2021, is even more powerful and can see galaxies that are 100 times fainter than those found by Hubble. Webb is expected to show objects from as far back as 180 million years after the Big Bang, which could be before the first galaxies even formed, and possibly from when the first stars were born. Scientists are also trying to detect a special kind of weak radiation called the 21 cm spinline radiation. This is an important tool for studying the early universe, even more useful than the cosmic microwave background radiation that has already been used to learn about the universe's beginnings. Researchers are still working to figure out the exact timeline of the first stars, galaxies, black holes, and quasars, as well as the precise start and end of the reionization period. New discoveries keep being made. For example, by 2019, scientists had confirmed galaxies like GNZ 11 that existed around 380 to 400 million years after the Big Bang. This shows that gas clouds formed stars much faster than previously thought. Observations of the Lyman Alpha Forest, a pattern of light changes from ancient objects, help scientists narrow down the timing of reionization and its end. But there is still much to explore in this area of research. In the Big Bang model, the formation of structures in the universe happens step by step, with smaller objects forming first before larger ones. The very first structures to appear were the first stars, called population 3 stars, tiny galaxies known as dwarf galaxies, and quasars. Quasars are extremely bright and active galaxies from the early universe, containing a supermassive black hole at their center, surrounded by a swirling disk of gas being pulled in. Before these structures began to form, scientists could study the universe using a simpler idea called linear cosmological perturbation theory. This idea suggested that the universe was mostly even, and any changes were just small differences. This made it easier to understand as the universe seemed mostly smooth. But once the first stars and galaxies started forming, things became much more complicated. Large groups of particles started to interact in more complex ways, so scientists needed more advanced methods to study it, like simulations using billions of particles called n-body simulations. The Bolshoi cosmological simulation is one of the most accurate examples of this. The population 3 stars were not just important for lighting up the universe, they were also responsible for turning the light elements formed during the Big Bang, like hydrogen, helium, and a small amount of lithium into heavier elements. These stars could be either very big or smaller, and they were made almost entirely of hydrogen and helium, with no heavier elements, which is why they're called non-metallic. The largest of these stars had short lives, burning through their hydrogen quickly, and exploding as supernovae after just a few million years. These explosions spread heavier elements into space, which would later form new generations of stars and planets. This marked the start of what's called the stelliferous era, the era of star formation. So far, no population 3 stars have been directly seen. Our knowledge about them comes from computer models that try to show how these stars would have formed and grown. However, scientists can still get clues about when star formation began by studying the cosmic microwave background radiation, which is leftover heat from the Big Bang. In 2016, observations made by the Planck Space Telescope suggested that the first stars started forming around 300 million years after the Big Bang. Quasars give us more clues about the early universe. The light from quasars contains elements like carbon, magnesium, iron, and oxygen. This means that by the time quasars appeared, there had already been a lot of star formation, including many generations of population 3 stars, which made those heavier elements. As these first stars, dwarf galaxies, and quasars slowly formed, the strong radiation they sent out started to reionize much of the universe. This process broke apart the neutral hydrogen atoms that filled space, turning them back into a plasma of free electrons and protons, something that hadn't happened since the universe's early stages, called recombination and decoupling. Reionization can be studied through quasars, which are extremely bright, active galaxies and some of the most powerful objects in the universe. Quasars help scientists understand the history of the universe because they give clues about how light interacts with different forms of hydrogen. In neutral hydrogen, electrons absorb ultraviolet light in specific patterns, called the Lyman series, which are linked to the energy levels of the electrons. But once hydrogen is ionized, it no longer has these energy levels. This means that light passing through ionized and neutral hydrogen will absorb light differently, showing different patterns of absorption. Ionized hydrogen in the space between galaxies, especially the electrons, can scatter light just as it did before reionization through a process called Thomson scattering. However, the universe had expanded and gas had clumped together into galaxies, so by the time reionization happened, the amount of ionized hydrogen wasn't enough to block all light. As light travels huge distances, billions of light years, from distant objects to Earth, any absorption by neutral hydrogen is stretched out, making it more red, a shift in wavelength by different amounts. This stretching lets scientists study the state of ionization during different times in the past. Reionization began as small bubbles of ionized hydrogen that grew bigger over time until eventually all the space between galaxies was ionized. When this happened, neutral hydrogen became much rarer. This process wasn't caused by light passing through galaxies or other dense areas, but was a result of the general state of the universe at that time. Reionization may have started around 250 million years after the Big Bang, a redshift of 16, and by around 500 million years, most of it was done, a redshift of 9 or 10. The last traces of neutral hydrogen were fully ionized by about 1 billion years after the Big Bang, a redshift of 5 or 6, which was when scientists stopped seeing the absorption patterns that show the presence of neutral hydrogen. After this, the universe has remained mostly ionized, with only a few neutral hydrogen clouds left, which make features called Lyman alpha forests in the light we observe today. While we now know the rough time when reionization happened, we still don't fully know what caused it. To ionize hydrogen, energy greater than 13.6 electron volts is needed, which comes from ultraviolet light with wavelengths shorter than 91.2 nanometers. This means the sources that caused reionization must have made lots of high-energy ultraviolet light. If the energy isn't constantly supplied, protons and electrons would recombine, which limits how long these sources could last and how many there were. Based on what we know, the most likely sources of energy for reionization are thought to be the first stars and galaxies, called population 3 stars, dwarf galaxies, and possibly quasars. Current estimates suggest that population 3 stars were the main contributors, with dwarf galaxies and quasars playing smaller roles. By the time reionization happened, the universe had expanded and matter was spread out. While hydrogen was reionized, the plasma was much thinner and light was less likely to scatter. This made the universe mostly see-through during reionization. The process ended as the universe became nearly fully ionized, though pockets of neutral hydrogen still exist in some areas, creating the Lyman alpha forests we can see today. Dark matter is a strange and invisible kind of matter that we can't see because it doesn't interact with light or any other kind of energy. We know it is there because of the odd effects it has on gravity, which can't be fully explained by the rules of physics unless there's more matter around than we can actually see. These strange effects show up when we study things like how galaxies form and change over time, how light bends around huge objects, called gravitational lensing, and even the way galaxies move within groups. We also notice its effect in the shape of the universe and the leftover energy from the Big Bang. In the most widely accepted model of the universe, known as the lambda CDM model, the universe's total mass and energy is made up of 5% regular matter, 26.8% dark matter, and 68.2% dark energy. That means dark matter makes up about 85% of the total mass, while dark matter and dark energy together make up 95% of the universe's total energy. We don't know exactly what dark matter is, but it doesn't seem to interact with regular matter or light, except through gravity, making it nearly impossible to find with the tools we have now. The main idea is that dark matter might be made up of tiny unknown pieces, such as weakly interacting heavy particles or axions. Another idea is that dark matter could be made of ancient black holes from the early universe. Dark matter can be sorted in different ways based on how fast its pieces move: cold, warm, or hot. Most scientists think dark matter is cold, meaning its pieces move slowly, letting them come together and form things over time. While most space scientists believe dark matter is real, some still question the idea. A small group of scientists puzzled by certain things that regular dark matter doesn't fully explain suggest that maybe the rules of gravity need to be changed. They've suggested other ideas like changed Newtonian motion or new kinds of gravity, but none of these ideas can fully explain all the proof we've found so far. This shows that, even if gravity needs some changes, dark matter still seems to be an important part of the puzzle. The idea of dark matter has a long and interesting past, filled with exciting findings and ideas that helped build our current understanding of the universe. The story begins with the work of some of the smartest minds in science starting in the late 19th century. In the year 1884, William Thomson, better known as Lord Kelvin, made some interesting guesses. He talked about the possible number of stars around our Sun in a book based on a series of talks he gave in Baltimore. Kelvin was trying to guess the number of stars near the Sun. He did this by studying how stars moved around our solar system. Using this information, he wondered what would happen if there were 1 billion stars within a distance of 1 kiloparsec from the Sun. At this distance, the stars would seem to move in ways that were hard to explain, and this idea led to more thinking about invisible matter in space. Lord Kelvin also guessed the Sun's age to be between 20 and 100 million years, which was later shown to be wrong. But his curiosity about the stars and how they move helped start early ideas about dark matter. A couple of decades later, in the year 1906, the French math and science expert Henri Poincaré used the name dark matter, or matière obscure, while talking about Lord Kelvin's work. Poincaré said that there might be hidden matter in the universe, but he also thought that this hidden matter would be less than the matter we can see. Even though his ideas were far from correct, Poincaré's use of the term dark matter brought the idea into the science world. In the 1920s, dark matter continued to interest skywatchers. In the year 1922, Dutch sky expert Jacobus Kapteyn became one of the first to use how fast stars move to suggest the existence of dark matter. He noticed that the way stars moved in space could be affected by unseen forces, hinting that invisible matter might be there. Then, in the year 1930, Swedish sky expert Knut Lundmark went further with the idea, realizing that the universe must have much more matter than we could see through our tools. This finding was important because it showed that the part of the universe we can see might not be the whole story. In the year 1932, another Dutch scientist, Jan Oort, joined the talk by saying that dark matter might be in our part of the galaxy. Oort studied how stars moved near our galaxy and decided that there must be more matter in our galaxy than we could see. But later, he found out that his numbers weren't fully correct, and more study would be needed to truly understand this unseen matter. Then, in the year 1933, Swiss space expert Fritz Zwicky made a major finding while studying groups of galaxies at the California Institute of Technology. Zwicky was looking at the Coma cluster, a large group of galaxies, and noticed something strange. The galaxies in the group were moving much faster than expected based on the matter we could see. This led him to say there must be a huge amount of invisible matter, which he called dunkle materie. Zwicky guessed that the Coma cluster had around 400 times more matter than could be seen through tools based on how the galaxies were moving. He believed that this unseen matter was causing the gravity that kept the galaxies in the group together. Even though Zwicky's numbers were far off, mainly because of old values, he was one of the first to correctly say that the universe must have unseen matter pulling things with gravity. Zwicky, however, had a different idea of dark matter than we do today. He thought that dark matter was just regular matter that didn't give off light, not something totally different like the strange dark matter we think about now. Still, his work was a big step toward discovering dark matter. As time went on, more signs of dark matter started to appear. One important piece came from studying how galaxies spin. In the year 1939, H.W. Babcock studied how the Andromeda galaxy spins. He found that the stars on the outer sides of the galaxy were moving much faster than expected. This showed that there was much more matter in the galaxy than could be seen by just looking at the stars. At first, Babcock thought that this strange spinning might be because light was being blocked inside the galaxy, or because the galaxy worked differently in its outer parts. But his study was an early clue that something invisible was changing the way the galaxy spun. The next year, in 1940, Jan Oort made another big discovery. He studied a galaxy called NGC 3115 and found a large, invisible cloud of matter around it. This was more proof that galaxies might have hidden matter we couldn't see with the tools we had at the time. The idea of dark matter really started to become popular in the 1970s. Many different science studies came together to show that galaxies might be surrounded by huge, invisible clouds of matter. In the year 1974, 2 different research teams, one from Princeton, New Jersey, led by Jeremiah Ostraker, Jim Peebles, and Amos Yahil, and another from Tartu, Estonia, led by Jan Einasto, Ensar, and Hans Kasich, came to the same idea on their own, making the idea stronger. One big clue that pointed to these invisible galaxy clouds was the way galaxies spin. Both regular tools and radio tools were very important in these findings. Vera Rubin and Kent Ford, using a new tool called a spectrograph, made better measurements of the speed of edge-on-spiral galaxies and found surprising results in how they spun. At the same time, radio scientists used special radio tools to study the 21 centimeter signal of hydrogen gas in nearby galaxies. Unlike starlight, which only comes from the middle parts of galaxies, hydrogen gas spreads much farther out. This lets scientists watch spinning patterns much farther from the center, giving a better idea of how much matter was really in a galaxy. Early studies of the Andromeda Galaxy, using big tools like the 300-foot Greenbank tool and the 250-foot Jodrell bank dish, showed that the hydrogen spinning curve didn't behave as expected from Kepler's rules, which describe how things move around a center of gravity. As tools got better, more advanced equipment let scientists measure even farther. In the year 1975, Roberts and Whitehurst went even farther, measuring the spinning speed of Andromeda all the way out to 30 kiloparsecs. Their results showed that the galaxy's spinning stayed flat even far from the center. This was important because it meant there was much more matter out there, beyond what we could see with regular tools. These findings, shown in their graphs, combined starlight data with the new hydrogen data, clearly showing the surprising flatness of how the galaxy spun on the outside. The solid line in the graph showed the starlight data, while the other line showed the total matter, which kept growing even in the farthest parts of the galaxy. At the same time, scientists were coming up with even better ways to study galaxies. Using interferometric arrays, many radio tools working together, researchers like Rogstad and Shostak in 1972 mapped the hydrogen spinning curves of 5 spiral galaxies. They found that all of these galaxies had flat spinning curves as well, meaning that the mass in the outer parts of the galaxies was much more than what could be explained by the stars and light we can see. By the late 1970s, most people in the field agreed that dark matter halos probably surrounded galaxies, and this became one of the biggest puzzles in space science. In the 1980s and 1990s, many observations began to suggest that dark matter was real. One important study done by Persic, Salucci and Stell in 1996 looked closely at 967 spiral galaxies and found strong proof that dark matter exists. Other backup evidence included strange things like gravitational lensing, where galaxy groups bend light from things behind them, the spread of hot gas in galaxies and groups, and the way small temperature differences, called anisotropies, show up in the cosmic microwave background, which is the leftover glow from the Big Bang. Today, most scientists agree that dark matter is made up of pieces that we haven't found yet, and these pieces are unlike anything we already know. The search to find this strange piece has become one of the biggest goals in particle physics, with many scientists using different ways and tests to try and figure out the truth. To put it simply, when scientists talk about matter in the universe, they're talking about anything that adds to the total energy, and its thickness changes in a certain way as the universe grows. Specifically, it gets thinner as the cube of the growth, meaning the more the universe stretches, the less matter there is in each area. This is not the same as radiation, which gets thinner even faster. Its energy gets weaker as the universe grows, following the opposite of the fourth power of the growth. On the other hand, the cosmological constant acts differently. It stays the same no matter how much the universe stretches, meaning its energy thickness stays constant. This difference in how matter, radiation, and the cosmological constant act is because of something called radiation redshift. To picture this, imagine the universe getting bigger. If the size of the universe we can see doubles, the scale factor of growth also doubles. Because of this, the energy of things like the cosmic microwave background radiation, the glow left over from the Big Bang, gets weaker because each light piece, photon, has to stretch out over a bigger space, lowering its energy. The same thing happens to very fast-moving pieces, like the early neutrinos. They also lose energy in a similar way. But the cosmological constant, which is part of space itself, doesn't change no matter how much the universe grows. When we say dark matter, we're usually talking about parts of the universe that we can't see, but still have mass and follow similar rules as regular matter. However, more specifically, dark matter is often used to talk about a special kind of invisible matter that isn't made of the usual particles we already know, leaving out something called missing baryons. The meaning of dark matter can change depending on how it's used. The arms of spiral galaxies spin around their center, and as you move farther from the center, the amount of visible mass in the galaxy goes down. If all the galaxy's mass were visible, it would act like a simple system where most of the mass is in the center and things move around it, like planets around the sun in our solar system. Based on Kepler's third law, we'd expect these things to move more slowly the farther out they are, just like how the planets farther from the sun move slower. But that's not what we see in galaxies. Instead, the spinning speeds of stars and gas in a galaxy stay the same, or even go up the farther out you go from the center. To explain this strange finding, it's clear that the spread of mass in spiral galaxies is not like the solar system. In fact, there may be a lot of invisible, non-glowing matter, what we call dark matter, on the edges of the galaxy. In systems that stay together, like galaxies, the stars also follow a rule called the virial theorem. This rule helps explain how mass is spread out in a system by looking at the speeds of the stars. When astronomers look at how fast stars are moving in systems like elliptical galaxies or tightly packed star groups, they can use this rule to figure out how the mass is spread out. But in many cases, the measured speeds don't match what we'd expect from the amount of visible mass in the system, even when we think about the star's complex orbits. Just like with the spinning curves of galaxies, the best way to explain this difference is that there's more invisible matter involved. Again, dark matter. Galaxy groups are very useful in studying dark matter because we can measure their mass in 3 different ways. By looking at how fast the galaxies in the group are moving, by studying the X-rays coming from the hot gas in the group. By studying these X-rays, we can find the temperature and thickness of the gas, which lets us figure out the pressure. Using the balance between gravity and pressure, we can find the total mass of the group. By using gravitational lensing, where the mass of the group bends light from things behind it. This lets us measure the group's mass without needing to see how its galaxies are moving. All 3 of these ways give us the same result. Dark matter makes up about 5 times more mass than all the matter we can see in these groups. One interesting result of Einstein's idea of general relativity is something called gravitational lensing. This happens when huge things like galaxies or galaxy groups sit between a light source and the person looking at it. These big things act like a lens, bending the light that passes through them, making the light from the source look bent or stretched. The key thing is that gravitational lensing only needs mass to happen. It doesn't matter what the mass is made of. The bigger the mass, the more it bends the light. For example, think of a galaxy group between us, and a very far away object like a quasar. The group of galaxies will bend the light from the quasar, making it look different. When we talk about strong lensing, we mean the big clear way light from background galaxies can bend into arc shapes as it goes through a large object's gravity field. This has been seen around many faraway galaxy groups, including one called Abell 1689. By studying the shapes of these arcs, scientists can figure out how much mass the galaxy group has. In weak lensing, the bending is much smaller, and galaxies don't turn into arcs. Instead, we see tiny changes in their shapes. By studying these small changes, scientists can learn about how dark matter is spread across the universe. The patterns of mass and light in these studies match what we expect from dark matter studies. Now, while both dark matter and regular matter are types of matter, they act very differently. In the early universe, regular matter had electric charge and interacted a lot with light, which caused it to scatter. But dark matter doesn't interact with light, even though it still affects the universe in other ways. For example, it pulls on things through gravity, especially across huge distances, and changes how regular matter moves and spreads out. Because of these differences, regular matter and dark matter grow and change in different ways, leaving separate marks on the cosmic microwave background. The cosmic microwave background is almost like a perfect blackbody, meaning it gives off a smooth, even temperature. But there are tiny temperature changes, about 1 part in 100,000, that scientists can study. These small differences, called anisotropies, can be mapped out across the sky. When scientists turn this map into a graph called the angular power spectrum, they see a bunch of peaks that are evenly spaced but have different heights. The exact spots of these peaks depend on key things in space science, and by comparing these spots to ideas in theory, we can learn more about what the universe is made of. The first time scientists found these small changes in the cosmic microwave background was in 1992 using the COBE satellite, but it couldn't show the peaks clearly. In 2000, the Boomerang experiment using a balloon to take readings, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more clearly. What they found agreed with the lambda CDM model of space science. Structure formation is the process that began shortly after the Big Bang, when small uneven parts in the universe's thickness caused matter to fall together and form stars, galaxies, and groups of galaxies. Before this time, the universe was even, with no big differences in thickness, as described by the Friedmann answers to general relativity. Over time, tiny changes in thickness started to grow and stick together, turning the smooth, plain universe into a more detailed shape filled with stars and galaxies. In the early stages, light energy filled the universe and had a big effect on matter. This light energy stopped normal matter's thickness changes from growing and forming shape. If the universe only had normal matter, these changes would not have had enough time to grow into the galaxies and groups we see today. The key to fixing this problem lies in dark matter, which is not affected by light energy. This allowed its thickness changes to grow first, creating gravity wells that later helped normal matter fall into galaxies and other shapes. The pull from dark matter acted like a magnet, pulling in normal matter and speeding up the making of these large space shapes. A clear example of the effect of dark matter is the bullet cluster, formed by the crash of two big galaxy groups. What makes the bullet cluster especially interesting is the difference between where the mass of the group is found according to gravity bending, the bending of light around heavy objects, and where the matter we can see is found. This difference is hard to explain with other gravity ideas, which expect gravity bending to happen only around matter we can see. However, the usual idea of dark matter can easily explain this. The gas we can see in the groups, which reacts with light and other types of energy, was slowed down and cooled by electric forces during the crash. Dark matter, on the other hand, doesn't react with light in the same way, so it moves through the crash untouched, splitting from the gas we can see. This made two different gravity bending spots as seen. Along with dark matter, space scientists use Type Ia supernovae as standard candles to measure how far things are across the universe. These supernovae have a known brightness, so by checking how dim they look, scientists can find out how far away they are. This method has shown that the universe is growing faster and faster, something usually explained by dark energy. Baryon, acoustic oscillations, BAO, mean regular changes in the thickness of normal matter, baryons, in the universe, which happened on large scales in the early universe. These changes were caused by sound waves moving through the hot, thick mix of light particles and baryons before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background light. As the universe grew, dark matter and normal matter began to stick together, but the effect of the first changes got weaker over time. However, we can still see a small pattern where galaxies are more likely to be spaced about 147 million light-years apart, which is a small but measurable sign of these early changes. This pattern was guessed in the 1990s and proven in the year 2005 through large galaxy surveys like the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey. By putting together cosmic microwave background results with BAO measurements, scientists can get a clear estimate of important universe numbers, like how fast the universe is growing and how much matter it has. These results support the lambda CDM idea, which is the main theory of how the universe works today. Big surveys of galaxy redshifts help us make a 3-dimensional map of where galaxies are across the universe. But these maps are not perfect because the distances we guess are based on the redshift we see. The redshift we measure is affected by two things. The main reason is the universe's growth, but there's also a smaller effect from the galaxy's own motion, called its peculiar speed. In general, superclusters, groups of many galaxies, are growing more slowly than the average growth of the universe because their gravity is pulling things inward. On the other hand, empty areas, huge spaces with very few galaxies, are growing faster than the universe as a whole. This difference in growth causes some interesting effects. For example, galaxies that are in front of a supercluster are moving toward it faster than expected, so their redshift will be a little higher than we would normally expect for their distance. In contrast, galaxies behind the supercluster seem to have a slightly lower redshift than expected. This difference makes superclusters look flattened when we look straight at them, while empty areas look stretched. But this effect is hard to see in one single shape. since we don't know its exact look. Instead, scientists can see this effect by averaging results from many shapes. The effect was first guessed by Nick Kaiser in the year 1987 and was later proven in the year 2001 by the 2-degree field galaxy redshift survey, with results matching what we expect from the lambda CDM idea of the universe. In a similar area of study, the Lyman alpha forest is the group of light-absorbing lines found in the light spectra of faraway galaxies and quasars. These lines are made by neutral hydrogen blocking light at a certain light wave, called the Lyman alpha transition. Looking at the Lyman alpha forest helps space scientists test and improve their universe ideas, with results that agree with the WMAP findings. Dark matter is often split into 3 types: cold, warm, and hot. These names don't mean temperature, but instead describe how fast the particles were moving in the early universe. Simply put, they show how far the particles moved around by chance before the universe started growing and slowing them down. This distance is called the free streaming length, FSL. The kind of dark matter depends on how this FSL compares to the size of a protogalaxy, an early space object that would later become a small galaxy. If the FSL is much smaller than the size of a protogalaxy, it's called cold dark matter. If it's about the same size, it's warm dark matter, and if the FSL is much bigger, it's hot dark matter. Some ideas suggest a mix of these types, which were more common in the middle of the 1990s, but became less popular after the discovery of dark energy. The main idea behind the free streaming length is that, after the Big Bang, the universe started with small thickness changes, caused by tiny random changes at the smallest levels. As these particles moved from thicker areas to thinner ones, the fast growth of the universe limited how far they could go. Faster particles, like those in hot dark matter, could move further before the universe got too big, while slower particles, like those in cold dark matter, couldn't go very far. This means that the free streaming length sets a limit on how big the shapes in the early universe could get. Hot dark matter would lead to the making of large shapes, like superclusters, which would later break into galaxies. Cold dark matter, however, allows smaller shapes like galaxies to form first. Recent observations, especially deep space pictures, show that galaxies formed first, followed by galaxy groups and superclusters as galaxies came together. This supports the idea that most dark matter is cold, not hot. This is also why neutrinos, which move nearly at the speed of light and would be hot dark matter, cannot explain most dark matter. Dark matter means any kind of matter that pulls on regular matter, like stars and planets, mostly through gravity. This means that dark matter might not be a totally new type of particle, but could, in theory, include normal matter like protons or neutrons. In fact, many things space scientists already know, like planets, brown dwarfs, red dwarfs, stars, white dwarfs, neutron stars and black holes, fit into this group. For example, when a black hole pulls in matter, it doesn't tell the difference between normal matter, like protons, and other kinds. Once it's inside the event horizon, all matter is treated the same. These hard-to-see objects are called MACHOs, massive compact halo objects. Some scientists once believed that MACHOs made up most of dark matter, but this idea has now been mostly rejected. There is strong proof showing that most dark matter is not made of normal visible matter. First, if there were enough normal matter like gas or dust spread around, we would be able to see it when starlight shines on it. But we don't see this kind of matter in the amounts we would expect. The Big Bang theory helps us understand how the elements we observe today were created. According to this theory, if there were more normal matter, called baryons, in the early universe, we would have seen a higher amount of elements like helium, lithium, and other heavier elements. Based on what we observe, we know that only about 4 to 5% of the universe's total mass consists of this regular matter. However, large-scale studies of galaxies and other cosmic structures show that the total amount of matter is about 30% of what is needed to keep the universe stable. Further investigations have shown that only a small portion of dark matter seems to be in the form of regular hidden objects, like small planets or black holes, called MACHOs. Studies involving the bending of light by gravity, gravitational microlensing, suggest that these objects can't account for the majority of dark matter, as their masses fall within a range that excludes nearly all of the likely possibilities. Detailed studies of the cosmic microwave background, the faint radiation left over from the Big Bang, by missions like WMAP and Planck, provide strong evidence that about 5/6 of the matter in the universe doesn't interact much with light or regular matter, except through gravity. This suggests that dark matter is largely invisible and can only be noticed through its gravitational pull. If regular matter, called baryonic matter, doesn't account for most of dark matter, then dark matter must be made of something else, specifically non-baryonic matter. There are two main possibilities for non-baryonic dark matter: new, unknown particles and ancient black holes from the early universe. Unlike regular matter, these non-regular particles don't help create the elements that formed during the Big Bang, a process known as Big Bang nucleosynthesis. Instead, we only notice them because of the gravitational effects they cause, such as how they bend light, called weak lensing. Some types of dark matter can even interact with each other, self-interacting dark matter, or with normal particles like WIMPs, weakly interacting massive particles. These interactions might produce detectable signs, such as gamma rays and neutrinos, which scientists could possibly see, indirect detection. There are many different candidates for dark matter, each with its own strengths and weaknesses. WIMPs don't have a strict definition, but they are generally thought of as basic particles that interact through gravity, and possibly other weak forces, such as the weak nuclear force. Many theories suggest that WIMPs were created in the early universe in a similar way to regular particles. These particles would make up what's called cold dark matter. To explain how much dark matter we have today, the WIMP particles would need to be able to destroy each other in a specific way, which matches what would happen if they had masses around 100 billion electron volts and interacted through the electroweak force. This idea is often called the WIMP miracle, because it fits so well with predictions from supersymmetric theories, which extend the standard model of particle physics. A stable partner particle from supersymmetry has long been seen as a main candidate for dark matter. Researchers are working hard to find WIMPs by looking for the products of their destruction, such as gamma rays, neutrinos, and cosmic rays coming from nearby galaxies. They also use experiments designed to directly detect WIMPs in laboratories by measuring their interactions with atomic nuclei, or by trying to create WIMPs in particle smashers like the Large Hadron Collider, LHC. However, in the early 2010s, experiments didn't find strong proof for supersymmetry, and the LHC results cast doubt on the simplest WIMP ideas. Axions, another candidate for dark matter, are theoretical particles that were first suggested in 1978 by Frank Wilczek and Steven Weinberg. These particles were originally suggested to solve a problem in the theory of quantum chromodynamics, which explains how quarks and gluons interact. Axions are incredibly light and weakly interact with other particles, making them a perfect candidate for dark matter. They could be produced in the early universe and would stay present today, their amount depending on their mass. Axions are thought to be so light that they could help explain some of the small-scale issues in the lambda CDM model, the main cosmological model. The axion theory has gained support in recent years, especially after WIMPs were not found. The axion's extremely low mass means that quantum effects could possibly explain the small-scale mysteries of dark matter. Primordial black holes, another interesting idea, are thought to have formed in the very early universe, right after the Big Bang. During the time of fast expansion known as inflation, incredibly dense areas of tiny matter could have collapsed under their own gravity, creating black holes without the need for a star's death, as is the case with regular black holes. These black holes would come before the first stars and could have masses ranging from tiny, even as small as atoms, to incredibly large, far beyond typical stellar black holes. The idea of primordial black holes was first suggested in 1967 by Yakov Zeldovich and Igor Novikov, and later by Stephen Hawking in 1971. The idea quickly gained support as a possible explanation for dark matter. One of the advantages of primordial black holes as dark matter candidates is that the theory behind black holes is already well known in physics, general relativity, and black holes themselves are already known to exist. However, creating primordial black holes might require difficult conditions, such as rare forms of cosmic inflation or theories beyond the standard model of particle physics. In 2015, gravitational wave measurements from the detection of black hole mergers brought new interest in primordial black holes as dark matter. Some black holes found by these experiments had masses that seemed too large to be formed by the usual processes, like the collapse of a star. This suggested they could be primordial. However, a study that looked for signs of gravitational lensing from middle mass black holes, expected to be dark matter, found no proof for them, although some researchers suggest this could be due to guesses about the mass of these black holes. Further observations, like those made by the James Webb Space Telescope, may give more clarity on this idea. Scientists once thought that incredibly small black holes, known as primordial black holes, might make up a large portion of dark matter. However, the Voyager 1 spaceship, which explored beyond the Sun's influence, measured the flow of positrons and electrons and found something surprising. The amount of particles seen was too low, and their energy levels were not what scientists expected. This led researchers to decide that these tiny black holes are too rare to account for dark matter. Despite this, the idea of dense forms of dark matter continues to be studied, with new ideas even suggesting ways to cool dark matter. As of 2018, the mystery remains unsolved. In 2019, further observations of the Andromeda Galaxy showed no signs of microlensing effects, which would be expected if tiny black holes were present, adding more doubt to their existence. However, there's still a gap in our understanding. There is a range of mass smaller than what we can currently detect with optical microlensing, where primordial black holes could possibly make up all of the dark matter. This area remains open for study and continues to challenge our understanding of the universe. If dark matter is made of particles that barely interact with anything, an important question arises. Could these particles form objects like planets, stars, or black holes? In the past, the answer has been no, and there are two main reasons for this. It can't easily lose energy. Regular matter forms dense objects like stars and planets because it can lose energy in many ways. For example, when particles fall inward due to gravity, they can lose energy, which allows them to slow down and gather into more stable objects. Dark matter, however, doesn't seem to have the ability to lose energy because it doesn't interact with other matter strongly except through gravity. Without ways to release energy, dark matter particles that start to get pulled inward would just heat up, speed up, and eventually escape, stopping the formation of compact objects. It doesn't interact in diverse ways. Regular matter interacts through many forces, such as gravity, electromagnetism, and the strong nuclear force, allowing it to form complex structures like atoms, stars, and galaxies. For instance, inside stars, particles interact through nuclear fusion, giving off light and neutrinos. In dark matter, we don't see proof for such interactions beyond gravity, and possibly some weak interactions, but this is still a guess. Without these varied interactions, dark matter doesn't have the ability to form the kinds of structures that regular matter does. If dark matter is made of very small particles, these particles pass through every square centimetre of Earth millions or even billions of times every second. Many experiments are trying to test this idea, while WIMPs, weakly interacting massive particles, have been the most commonly searched for options. Axions are also getting attention, especially in projects like the Axion Dark Matter Experiment, ADMX. Other possibilities include heavy particles from a hidden group that only interact with regular matter through gravity. There are two main types of experiments studying dark matter: direct detection experiments. These look for signs that dark matter particles are hitting atomic nuclei in a detector. The goal is to measure tiny energy changes, a few thousand electron volts, caused by these hits. When dark matter hits an atom, the atom might give off energy as light or vibrations, which can be measured. To work well, these experiments need to be as free as possible from outside interference, which is why they are often done deep underground, where cosmic rays don't disturb them. Important underground labs include Stowell Mine, Sudan Mine, and the Gran Sasso National Laboratory. These experiments often use two kinds of detectors: cryogenic detectors that measure heat from particle collisions in materials like germanium, noble liquid detectors that detect light made when a particle hits liquids like xenon or argon. Well-known experiments in these areas include CDMS, CREST, Xenon, and LUX. These detectors are especially good at telling dark matter apart from background particles, which mostly hit electrons, while dark matter hits atomic nuclei. Indirect detection experiments. These look for the effects of dark matter particles destroying each other or breaking apart. So far, no direct detection experiment has confirmed dark matter, but these studies have helped narrow down what dark matter could be like. One interesting result comes from the Dama Ne and Dama Libra teams, which noticed a yearly change in their data, maybe because of the Earth moving through a dark matter cloud. However, other experiments like LUX and Super CDMs haven't seen the same change, creating a small mystery. There are also special experiments that track the movement of dark matter particles based on how the solar system moves around the centre of the galaxy. This method tries to separate dark matter signals from background noise, which should be evenly spread out. Experiments like DMTPC and drift try to detect the direction dark matter is moving to help find possible signals. Indirect detection experiments aim to find signs of dark matter by looking for what happens when dark matter particles break apart in space. In areas with a lot of dark matter, like the centre of the Milky Way, two dark matter particles might collide and destroy each other, giving off gamma rays or pairs of normal particles and their opposites, antiparticles. If a dark matter particle is unstable, it might break into normal particles or others, which could be detected indirectly through extra gamma rays, antiprotons or positrons from areas with a lot of dark matter, like the Milky Way's centre or faraway galaxies. One challenge is that other space events could make similar signals, so multiple observations from different places are needed to confirm dark matter. Dark matter particles that pass through the Sun or Earth might interact with atoms and lose energy. This could make dark matter collect at the centres of these bodies, increasing the chances for collisions. These events could send out high-energy neutrinos, which could be strong evidence for dark matter made of WIMPs. Instruments like Amanda, IceCube and Antares are looking for these signals. Also, the detection of gravitational waves by LIGO in 2015 opened new ways to study dark matter, especially if it exists as early black holes. Several experiments have tried to detect dark matter emissions like those from collisions or breakdown. For example, the Energetic Gamma Ray Experiment Telescope saw more gamma rays in 2008 than expected from the Milky Way, but scientists thought this was because of errors in estimating the telescope's sensitivity. The Fermi Gamma Ray Space Telescope is continuing this search. In 2009, it saw extra gamma rays from the centre of the Milky Way, which could come from dark matter collisions or an unknown group of pulsars. In 2012, a deeper study of Fermi data suggested a 130 giga-electron-volt signal from the Milky Way's centre, which could come from WIMP collisions. At even higher energies, ground-based telescopes have set limits on dark matter collisions in small galaxies and galaxy groups. The Pamela experiment, launched in 2006, saw an unusual amount of positrons, which might come from dark matter or pulsars, though no extra antiprotons were found. Similarly, the Alpha Magnetic Spectrometer on the International Space Station measured high-energy cosmic rays in 2013, possibly linked to dark matter collisions. Another way to find dark matter is to try to make it in a lab. Experiments like those at the Large Hadron Collider, LHC, may create dark matter particles when protons collide. Because dark matter doesn't interact much with normal matter, it might be noticed indirectly by seeing large amounts of missing energy, while other particles from the collision are measured. The LP experiment, using a similar method but studying dark matter and electrons, also gives limits on dark matter. Any discovery of dark matter in such experiments must be confirmed by indirect or direct detection experiments to be sure it is really dark matter. Because scientists still don't know exactly what dark matter is, many other ideas have been suggested to explain the strange things we see in the universe. One big clue pointing to dark matter comes from general relativity, which explains how gravity works. This theory has been tested many times and works very well for things in our solar system. But when scientists use it for entire galaxies or the universe, it hasn't been fully proven to work the same way. Some researchers think the problem might not be missing matter, but the rules of gravity themselves. In other words, instead of searching for invisible dark matter, maybe we just need to change gravity's rules to match what we see. Over the years, different ideas have been suggested as alternatives to dark matter. Some well-known ones include MOND, modified Newtonian dynamics, TVs, a more detailed version of MOND, FR gravity, negative mass, dark fluid, and entropic gravity. The big problem with these alternative ideas is that clues for dark matter come from many sources. For example, we see its effects in how galaxies move, how light bends around big objects, how the universe grows over time, and more. An alternative idea might explain one or two of these, but it is very hard to explain all of them without dark matter. Still, some of these new ideas have shown small signs of promise. In 2016, scientists did a test related to gravitational lensing, the bending of light by gravity, that gave some support to entropic gravity. In 2020, another study found results that seemed to match Mond's predictions. Even though these are interesting, most space scientists still think dark matter exists, even if we don't know exactly what it is yet. While changing gravity's rules might explain some things, the large amount of evidence overall points to dark matter being real in some form. One of the most important discoveries ever made in science is realizing that the universe is not fixed or unchanging. Instead, it is always growing. It is expanding all the time. This amazing idea changed the way we understand the whole universe. For thousands of years, many people believed that the universe had always been the same, that it was eternal and unmoving. But now, we know that the universe has a history, a beginning, and that it is still changing. The proof that the universe is expanding is strong and convincing. It comes mainly from careful studies of light coming from faraway objects in space, and from our deep understanding of how gravity and light behave. To really understand how scientists discovered this, we need to look at the history of astronomy, the ways used to study the skies, and what this discovery tells us about the nature of everything around us. Before the 20th century, most scientists and thinkers believed the universe was static. It neither grew nor shrank. Even Sir Isaac Newton's famous laws of gravity had trouble explaining how a steady, unchanging universe could last forever. According to his laws, gravity would eventually pull everything together unless the universe was either endlessly large or perfectly balanced in every direction. But the idea of an endless universe led to its own set of strange problems. Then, in the early years of the 20th century, Albert Einstein developed his groundbreaking theory of general relativity. This theory showed that gravity is not just a force, but actually comes from the bending or curving of space and time. However, Einstein's original equations did not describe a still, unchanging universe. They suggested that the universe should either be expanding or shrinking. At the time, this made Einstein uneasy, since the idea of a changing universe went against what most scientists believed. To fix this, he added an extra part to his equations called the cosmological constant. This part acted like a force that pushed outward, balancing gravity and keeping the universe still. Later in life, Einstein called this change one of the biggest mistakes he ever made. Around the same time, a Dutch astronomer named Willem de Sitter found a different answer to Einstein's equations. He showed that even in an empty universe, with no stars, planets, or galaxies, space could still expand by itself. This was a major clue that the universe might not be as still as people thought. But these early ideas were just theories. There was no real proof yet that the universe was expanding. The first real step toward discovering the universe's expansion came from an American astronomer named Vesto Slipher. Starting in the year 1912, Slipher began measuring the light from mysterious glowing clouds in space called nebulae. Back then, scientists thought these nebulae were just gas clouds inside our own Milky Way galaxy. But something strange appeared in the light. Slipher found that the light from most of these nebulae was stretched out, or shifted, toward the red part of the spectrum. This effect, called redshift, meant that the objects were moving away from Earth. A few of the nebulae showed blue shift, meaning they were moving toward us. By the year 1917, Slipher had measured the speeds of 25 nebulae, and most were rushing away at very high speeds. Slipher didn't say that this meant the whole universe was expanding, but his careful measurements laid the groundwork for one of the greatest discoveries in astronomy. Then came Edwin Hubble, another American astronomer. Building on Slipher's work, Hubble made two groundbreaking discoveries using the powerful 100-inch Hooker telescope at Mount Wilson Observatory in California. First, he looked closely at some of those spiral nebulae and discovered something amazing. Inside the Andromeda Nebula, he found a type of star called a Cepheid variable. These stars regularly grow brighter and dimmer over time, and their pattern of flickering is linked to their true brightness. By measuring how bright they look from Earth, and comparing that with how bright they really are, Hubble could figure out how far away they were. When he calculated the distance to the Cepheids in Andromeda, he realized the nebula wasn't part of our Milky Way at all. It was a separate galaxy, located far beyond the edge of our own. This discovery, made in the early 1920s, completely changed our view of the universe. For the first time, scientists understood that the Milky Way was just one of countless galaxies scattered across the vastness of space. Next, Hubble combined his new distance measurements with Slipher's earlier redshift data. In the year 1929, he published a stunning result. Galaxies that are farther away are also moving away from us faster. This became known as Hubble's law, and it showed for the first time that the universe was expanding. The farther away a galaxy is, the faster it seems to be moving away. This could be described with a simple equation. The galaxy's speed equals its distance multiplied by a number called the Hubble constant, which tells us how fast the universe is expanding. Hubble's discovery marked a turning point in science. It gave us the first clear proof from observation that the universe is not standing still. It is growing larger with time. To understand why redshift is so important, think of how sound works. When an ambulance drives toward you, the siren sounds higher in pitch. As it passes and moves away, the pitch drops. This is called the Doppler effect, and it happens because the sound waves are squished when the ambulance comes closer and stretched when it moves away. Light works in a similar way. If a light source moves away, its light waves get stretched, making the light look redder. If it comes toward you, the waves are squeezed and the light looks bluer. But with very distant galaxies, the redshift is caused by something even stranger. Not by motion through space, but by space itself expanding. Think of dots drawn on a balloon. When you blow up the balloon, the dots move farther apart. They aren't moving on their own. It's the balloon's surface that is stretching. In the same way, galaxies aren't speeding through space. They're being carried apart as the very fabric of space stretches. As light travels from a faraway galaxy, it moves through this expanding space, and the light waves stretch out too. The more space stretches while the light is travelling, the more the light gets redshifted. So when astronomers see highly redshifted galaxies, they're seeing light that left those galaxies a long time ago, when the universe was much younger and smaller. In the decades that followed, scientists found even more proof of the universe's expansion. A big breakthrough came from studying type Ia supernovae, which are huge explosions that happen when a white dwarf star in a pair system gains too much material from its companion and explodes. These explosions always happen at the same mass, which means they all have almost the same true brightness. Because of this, type Ia supernovae can be used as standard candles, objects with known brightness that help astronomers figure out distances. By comparing how bright they look with how bright they really are, scientists can calculate how far away they are. In the late 1990s, astronomers used these supernovae to study galaxies billions of light years away. They expected to find that the universe's expansion was slowing down due to gravity. Instead, they were shocked to discover that the expansion was speeding up. This surprising finding led to the idea of dark energy, a mysterious force that seems to be pushing the universe apart faster and faster. No one knows exactly what dark energy is, but its effects are clear, and it now makes up about 70% of the total energy in the universe. The discovery of dark energy was a stunning confirmation that the universe is not only expanding, it is speeding up. From the first hints in Einstein's equations to Slipher's early redshift data, to Hubble's clear proof from observation, and finally to the discovery of speeding expansion caused by dark energy, our understanding of the universe has grown a lot in just over 100 years. What once seemed like a calm, eternal sky is now seen as a dynamic, restless universe, expanding, changing, and full of secrets yet to be uncovered. The idea that our universe is expanding has very deep and fascinating consequences, especially when we think about the past. If space is growing larger today, that means it must have been much smaller a long time ago. If we keep looking backward in time, we eventually reach a moment when everything, all matter, energy, light, and even space itself, was squeezed into an unimaginably tiny, hot, and dense state. Scientists call this moment the Big Bang singularity, and it marks the start of everything we know: space, time, energy, and matter. It wasn't an explosion in space, it was the very beginning of space and time itself. This discovery changed everything. It meant that the universe wasn't always here in its current form. It's not eternal and unchanging. It's a living, changing place. The fact that space is expanding tells us that the universe has a limited age. It had a starting point, and from that beginning, it's been growing and changing ever since. To figure out how old the universe is, astronomers look at how fast it is expanding. They use something called the Hubble constant, which tells us the rate at which galaxies are moving away from each other. By working backward, like rewinding the universe's growth, they can estimate when it all began. Early on, scientists used just the Hubble constant to do this, But over time they added more details, like how much matter the universe contains and the strange effects of something called dark energy, which seems to be speeding up the expansion. Thanks to these improvements, today's best estimates say that the universe is about 13.8 billion years old. That number matches many other kinds of measurements and evidence, which is a good sign that we're on the right track. But there's something really important to understand about this expansion. It's not that galaxies are flying through space like rockets. Instead, space itself is stretching, and the galaxies are being carried along with it, like raisins moving apart in rising dough. That's why galaxies that are very far away from us appear to be moving faster, not because they're travelling fast on their own, but because there's more space expanding between us and them. There are exceptions to this rule on smaller scales. For example, the Andromeda Galaxy, which is about 2.5 million light-years away, is on a collision course with our own Milky Way galaxy. This is because gravity is strong enough between them to pull them together, even though space is expanding. On the larger scale of galaxy clusters and beyond, though, the expansion wins and galaxies keep drifting apart. One of the most astonishing ideas in modern astronomy is that the universe has no real centre and no clear edge. No matter where you are, it feels as if you are at the very heart of the cosmos. That's because space itself is stretching everywhere at once, in all directions. Imagine blowing up a balloon covered in tiny dots. The dots move away from each other no matter which dot you pick. This idea supports an important scientific rule called the cosmological principle, which says that, on the larger scales, the universe looks pretty much the same wherever you are and whichever way you look. In simple terms, the universe is homogeneous, meaning it is roughly the same everywhere, and isotropic, meaning it looks the same in every direction. We can actually see evidence of this cosmic stretching when we gaze deep into the night sky. Light doesn't travel instantly, it takes time to reach us. That means the farther away a galaxy is, the older the light we see from it. When we look at galaxies extremely far away, we are seeing them as they were billions of years ago. And what do these distant galaxies look like? They are smaller, more chaotic, and often irregular in shape compared with galaxies around us today. Their stars were forming at different speeds, and their chemical makeup was simpler. This tells a clear story. Galaxies started out simple and slowly evolved into the complex organized structures we see now. It's a snapshot of the universe growing, changing, and unfolding over time. Even more spectacular are quasars, the blazing, brilliant centers of young galaxies powered by supermassive black holes. Most quasars we see are incredibly far away, meaning they were far more common in the early universe. Their existence paints a picture of a cosmos that was once far wilder, more energetic and chaotic than it is today. Yet, not everything is fully understood. One of the biggest puzzles in modern astronomy is the Hubble constant, the number that tells us how fast the universe is expanding. Scientists have several ways to measure it, by studying nearby stars, exploding supernovae, or the faint afterglow of the Big Bang called the cosmic microwave background. Strangely, these different methods don't all give exactly the same answer. This mismatch is called the Hubble tension. It might simply come from tiny errors in measurements, or it could mean there is something fundamental about the universe we still don't understand. Some scientists even think it could point to entirely new physics beyond our current theories. That is why astronomers are using ever more powerful telescopes and advanced tools to study the universe's expansion. They hope not only to solve the Hubble tension, but also to uncover the secrets of dark energy, the mysterious force that seems to be pushing the universe to expand faster and faster. Dark energy might hold the key to the ultimate fate of the cosmos, whether it will stretch endlessly, growing colder and emptier over unimaginable time, or whether its behavior might change in surprising ways, steering the universe toward a future we cannot yet imagine. In the very first moments after the universe was born, everything was pure energy, blazing, wild, and chaotic. There were no atoms, no stars, and no galaxies. Even the tiniest bits of matter we now take for granted, like protons and electrons, had not yet formed. The universe had just burst into existence in a sudden explosion called the Big Bang, and right after, it went through an incredibly fast period of growth called inflation. Before this, there was a time called the Planck era, a stage so mysterious and extreme that the normal rules of physics didn't work. Right after this lightning-fast expansion, The universe was like a boiling soup of pure energy and tiny particles. This soup was unimaginably hot, far hotter than the center of any star. In it, the first building blocks of matter started to appear. This was a turning point, a moment when energy began turning into real particles. Everything we see today, from stars to people, traces back to this change. To understand what happened then, we need quantum physics, which explains how particles behave at incredibly small scales and under extreme conditions. At that time, light particles called photons had so much energy that they could create matter out of nothing. According to Albert Einstein's famous equation, E=mc², energy can become mass, and mass can become energy. So when a photon had enough energy, it could turn into a pair of particles, for example an electron and its opposite twin, a positron. But if these two particles met again, they would destroy each other, turning back into photons. This constant back and forth, making and destroying particles, was happening all the time in the early universe. As the universe kept expanding, it started to cool down. The temperature decided which particles could appear. At first, it was hot enough to create even the heaviest particles, but as it cooled, only lighter particles could continue forming. The universe was like a cosmic dance floor, with particles being made and destroyed in perfect balance, a state physicists call thermal equilibrium. At these extreme temperatures, something else amazing might have happened. Scientists think that all the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces might once have been joined together as a single superforce. This idea is part of what scientists call grand unified theories, or GUTS. According to these ideas, in the earliest moments, especially during the Planck era, which lasted only a tiny fraction of a second, gravity may have already split off from the other forces. As the universe cooled, the remaining forces started separating from each other one by one. For instance, the strong nuclear force eventually separated from the electro-weak force, a moment crucial for forming protons and neutrons. Now, let's look at the most important early building blocks of matter, quarks and leptons. These are called fundamental particles because, as far as we know, they are not made of anything smaller. There are 6 types of quarks: up, down, charm, strange, top, and bottom. Quarks also have a special kind of charge called color charge. This doesn't mean real color, it's just a way to describe how they interact with the strong nuclear force. Protons and neutrons, the particles in the center of atoms, are made from quarks. A proton has 2 up quarks and 1 down quark, while a neutron has 1 up quark and 2 down quarks. Leptons are another key group of particles. The most familiar one is the electron, which has a negative electric charge. There are also heavier versions of the electron called the muon and tau, along with 3 types of neutrinos: the electron neutrino, muon neutrino, and tau neutrino. Neutrinos are strange, ghost-like particles that have no electric charge and interact so weakly that they can pass through entire planets without hitting anything. In the first split seconds after the Big Bang, the universe was a thick, blazing soup of quarks, gluons, and leptons, all moving around with their antiparticles. This state is called quark-gluon plasma. In this plasma, quarks hadn't yet joined into protons or neutrons. The universe was too hot, and quarks had so much energy that the strong nuclear force couldn't hold them together. They moved freely, bouncing off each other and exchanging gluons, which are the particles that carry the strong nuclear force. But this phase lasted only a tiny fraction of a second. As the universe kept expanding and cooling, the temperature finally dropped to about 1 trillion degrees Celsius. Then something huge happened. The strong nuclear force became strong enough to trap quarks together, forming protons and neutrons. This is called hadronization. From that point, quarks could no longer exist alone. They had to join into larger particles called hadrons. Among these, the most important were protons and neutrons, known as baryons because they are made of 3 quarks. But a mystery remained, maybe the biggest one. According to what we know, the Big Bang should have made equal amounts of matter and antimatter. For every quark, there should have been an antiquark. For every electron, a positron. If the balance had stayed perfect, all particles and antiparticles would have destroyed each other, leaving nothing but light, a sea of photons. In that case, no stars, no galaxies, and no people would ever have existed. But something tipped the scale. For some reason, there was a tiny imbalance. just a little more matter than antimatter. This tiny leftover, maybe one extra particle of matter for every billion pairs, was enough to make everything we see today. In the year 1967, a brilliant physicist named Andrei Sakharov described 3 key conditions needed for this imbalance, called baryogenesis, to happen. 1. Baryon number violation. There must be processes that can create or destroy baryons, like protons and neutrons, instead of always keeping their numbers fixed. 2. C and CP violation. The laws of physics must treat matter and antimatter differently in some way, especially when mirrored or reversed in time. 3. Out of equilibrium conditions. The universe had to be changing so fast, expanding and cooling, that particles couldn't keep up, letting asymmetries freeze in before being erased. Many theories try to explain this, including some based on grand unified theories or electro-weak baryogenesis, but the full answer is still unknown. What we do know is that this tiny imbalance made all the difference. It gave us a universe full of matter, not just light. As the universe cooled, leftover protons and neutrons began to settle down, but electrons and positrons were still everywhere, being made and destroyed by high-energy photons. Eventually, the universe cooled below the energy needed to make these pairs. At that point, the last wave of annihilation happened, and a small surplus of electrons remained. These surviving electrons would one day become part of atoms, orbiting the nuclei made of protons and neutrons. Meanwhile, neutrinos, the nearly invisible particles, had already stopped interacting with other matter. They had decoupled from the rest of the universe and now travel silently through space. Today, this ancient sea of neutrinos, the cosmic neutrino background, still exists, though it is almost impossible to detect. It is one of the last whispers from the lepton epoch, a time when particles danced through fire and light in the infant universe. In the earliest moments, one of the most important things was setting the balance between protons and neutrons. This delicate balance would later determine how the first light elements like hydrogen and helium formed. At first, when the universe was unimaginably hot, much hotter than the centre of any star, the forces of nature were extremely active, especially the weak nuclear force, which helps particles change from one form to another. During this stage, protons and neutrons could easily transform into each other. A proton could turn into a neutron by grabbing a positron, a positive electron, and releasing a neutrino, a nearly massless ghost-like particle. A neutron could also break down into a proton, an electron, and an antineutrino. These reactions happened so often that, for a while, the number of protons and neutrons stayed about the same. But as the universe expanded and cooled, these particle-changing reactions slowed down. Eventually, they became too rare to maintain the balance. Since neutrons are slightly heavier than protons, they began to decay more often, turning into protons, electrons, and antineutrinos. This caused the number of neutrons to gradually shrink compared to protons. By the time the universe was about 1 second old, the temperature had dropped to around 10 billion degrees Celsius. At this point, the weak nuclear interactions had slowed too much, and the swapping of protons and neutrons stopped. This is called the freeze-out of weak interactions. From then on, the ratio of neutrons to protons was fixed at about 1 neutron for every 6 or 7 protons. This ratio turned out to be extremely important, because almost all the remaining neutrons would soon end up inside helium nuclei, each with 2 protons and 2 neutrons, during Big Bang nucleosynthesis, which happened a few minutes later. The extra protons that didn't pair with neutrons became nearly all the hydrogen in the universe. This early decision set the stage for everything that followed, including stars, galaxies, and planets. At that time, the universe was still a hot, dense sea of particles, mostly free protons, neutrons, and electrons. It was also full of high-energy photons, particles of light carrying enormous energy. These photons were so energetic that atoms couldn't form. They constantly collided with charged particles, especially electrons and protons, keeping everything in a glowing, foggy state. This period is called the radiation-dominated era because light, not matter, had most of the energy in the universe and controlled how fast it expanded. In this very early stage of the universe, there were no atoms or stars yet, but something just as important had already happened. The basic building blocks of matter had been made, and their amounts had been decided. This early mix of particles and light set the stage for everything that would happen later in the universe. Without the right balance between protons and neutrons, and without radiation playing the main role in shaping how the universe worked, the cosmos we see today would have been very different. The universe is getting bigger over time, a discovery first made nearly 100 years ago. In the late 1920s, the astronomer Edwin Hubble saw that faraway galaxies were moving away from us, which meant the universe was expanding. This was a huge surprise, and it changed the way scientists understood the cosmos forever. For many years after Hubble's discovery, most scientists thought that although the universe was expanding, the pull of gravity from all the matter in it, stars, planets, gas, dust, and dark matter, would slowly slow it down. They pictured it like throwing a ball into the sky. At first it goes up quickly, but gravity eventually slows it and brings it back down. In the same way, they thought the universe's expansion would lose speed over time, and maybe even stop or reverse someday. But everything changed in the late 1990s. Two separate teams of scientists were studying very far away exploding stars called Type Ia supernovae. These explosions are extremely bright and always happen when a certain kind of star, a white dwarf, gathers too much material from a nearby companion and passes a limit called the Chandrasekhar limit. Because they always explode the same way, with the same brightness, astronomers use them as standard candles. That means they can figure out how far away they are based on how dim they look to us. When the scientists looked at these supernovae, they found something shocking. The faraway supernovae were dimmer than expected. That meant they were farther away than they should have been if the universe was slowing down. This surprising result showed that the expansion of the universe wasn't slowing down, it was actually speeding up. This unexpected discovery showed that there is a strange force pushing galaxies apart faster and faster. Scientists gave this force a name, dark energy. Today, dark energy is thought to make up about 68% of all the energy and matter in the universe, making it the largest and strongest part of our entire cosmos. Its effect reaches across time, shaping the past, present, and future of the universe. Interestingly, the idea of something like dark energy had already appeared in science almost 100 years earlier. In the year 1917, Albert Einstein added a special term to his new theory of general relativity. He called it the cosmological constant, and he used it to keep the universe steady, because back then, scientists thought the universe wasn't growing or shrinking. But when Hubble later showed that the universe was indeed expanding, Einstein called the constant his biggest mistake. For many years, the cosmological constant was forgotten, but it never completely went away. When scientists found out that the expansion of the universe was speeding up, the idea of the cosmological constant came back into the spotlight. Now it seemed Einstein's mistake might actually explain something very important about the universe. The two teams who discovered the accelerating universe were the Supernova Cosmology project, led by Saul Perlmutter, and the High Z Supernova Search team, led by Brian Schmidt and Adam Riss. Both groups worked separately, but they reached the same conclusion. Their findings were so important that in the year 2011, Perlmutter, Schmidt, and Riess were given the Nobel Prize in Physics. But supernovae weren't the only clue pointing to dark energy. Another strong piece of evidence comes from a faint glow left over from the early universe called the cosmic microwave background, or CMB. This radiation is like a snapshot of the universe when it was just about 380,000 years old. By studying tiny changes in the temperature of the CMB, especially certain patterns called acoustic peaks, scientists can learn about the shape of the universe and the amounts of different types of matter and energy in it. Data from space missions like WMAP and Planck showed that the universe is flat, which means parallel lines never meet or move apart even across huge stretches of space. For the universe to be flat, it must have a very specific total energy density. But when scientists added up all the visible matter and the invisible dark matter, they only got about 32% of what was needed. The missing 68% had to come from something else, and that something else was dark energy. More evidence comes from how galaxies and large structures are spread across the universe. Normally, gravity pulls matter together to form stars, galaxies, and clusters, but dark energy pushes space apart, slowing down this gathering process. By studying the number of galaxies and how they are grouped at different points in time, scientists can see the effect of dark energy. One especially important clue comes from something called baryon acoustic oscillations, or BAOs. These are like frozen sound waves from the early universe that left a clear pattern in how galaxies are spread out. Scientists use this pattern as a kind of standard ruler to measure the universe's expansion. These measurements also show that the universe is expanding faster and faster, just like the supernova and CMB data show. So, what exactly is dark energy doing? According to general relativity, gravity isn't caused just by mass, it's also affected by pressure. While normal substances like gas have positive pressure that pulls things together, dark energy has negative pressure. This unusual pressure does the opposite. It pushes space apart. One possible explanation is that empty space itself has energy, called vacuum energy. As space grows, more vacuum energy appears, keeping the energy density the same but increasing the total amount. This leads to more and more pushing, speeding up the universe's expansion. The simplest idea for dark energy is still Einstein's cosmological constant, just the energy of empty space. But quantum physics predicts that this vacuum energy should be much, much bigger, up to a trillion times greater than what we actually see. This huge difference is called the vacuum catastrophe, or the cosmological constant problem, and it's one of the biggest mysteries in science. Other ideas suggest that dark energy might not be constant at all. It could be something that changes over time, like a field that spreads across the universe and slowly changes. This kind of idea is called quintessence. It works a bit like the Higgs field, which gives particles their mass. If quintessence exists, it might explain why dark energy became important only recently in cosmic history. But proving this idea is hard, and scientists haven't yet found solid evidence for it. Another group of ideas suggests that maybe we don't need dark energy at all. Maybe gravity itself changes over large distances. These modified gravity ideas suggest that the laws of gravity we know from Einstein's equations work perfectly at small scales, like around stars and planets, but act differently over the huge distances between galaxies. These ideas are interesting, but they must match every observation we've made so far, which makes them hard to get right. What does all this mean for the future of the universe? If dark energy keeps acting like a cosmological constant, then the universe will continue to expand faster and faster forever. This future is called the Big Freeze or heat death. In this scenario, galaxies far away from us will disappear beyond our reach, pulled away faster than light can travel. Eventually, even nearby galaxies might get pulled apart. Stars will burn out, black holes will slowly vanish, and the universe will become a cold, dark, and empty place with nothing but slowly fading radiation. But there are other, more extreme possibilities. If dark energy becomes even stronger over time, it could lead to a disastrous end called the Big Rip. In this scenario, the force of expansion would grow so strong that it would tear galaxies, stars, planets, and even atoms apart. On the other hand, if dark energy weakens or reverses, gravity might take over again. The universe could stop expanding and begin to shrink, ending in a big crunch, a collapse back into a single point, the opposite of the Big Bang. Right now, all the evidence points to the cosmological constant being the best explanation. That means the Big Freeze is the most likely future of our universe. The idea of dark energy brings up a strange and puzzling question called the cosmic coincidence problem. This question asks, why is it that right now, in the present age of the universe, dark energy has become just as important as matter in its effect on the universe's expansion? Why not earlier or later? This is especially strange because dark energy has only become stronger than matter recently, on cosmic timescales. Billions of years ago, the universe was filled mostly with matter, and gravity caused this matter to gather together, forming stars, galaxies, and clusters of galaxies. If dark energy had been stronger than matter much earlier, the universe would have expanded too fast for galaxies to form at all. On the other hand, if dark energy had appeared much later, the universe would have stayed dominated by matter for a long time, and we might not be here now to ask these questions. So, why is dark energy becoming important right now, just at the time when intelligent life, like us, has appeared and can observe it? Is this just a strange coincidence, or is there some deeper connection between the conditions of the universe and the appearance of life? Some scientists think this could be explained by something called the anthropic principle, which says that the universe has the features it does because only certain kinds of universes can support life, and we naturally find ourselves in one of those. Others go further and suggest the multiverse, the idea that there may be many different universes, each with different features. In this view, we just happen to live in one where dark energy showed up at just the right time to let galaxies and eventually life form. This mystery is still one of the most fascinating unsolved questions in science today. The search to understand dark energy is one of the biggest and most exciting challenges in modern cosmology. Scientists all over the world are working hard to study it more closely. Over the next few years, several powerful space and ground-based telescopes will help us learn more. These include the Nancy Grace Roman Space Telescope, the Euclid Mission, and the Vera C. Rubin Observatory. These observatories are being specially made to collect precise data about how the universe has grown and changed over time. By carefully looking at how galaxies are spread out across space, and by studying the brightness of faraway exploding stars called supernovae, scientists hope to find out whether dark energy is truly a constant force, something that never changes, or if it might change over time. If dark energy does change, it could mean that we're dealing with something very different from what Einstein first called the cosmological constant. It might instead be something called quintessence, a kind of energy that slowly changes as the universe grows. These future discoveries could also help rule out some ideas that try to change or replace Einstein's theory of gravity altogether. Finding out what dark energy really is could completely change how we understand the universe. It could teach us new things about gravity, how tiny particles behave, and even about the ultimate fate of everything that exists. If we could somehow turn back time and go to the very first moments of our universe's existence, we would find ourselves in a world that is completely different from anything we know. It would be a place of unimaginable heat and extreme density, filled with a bubbling, glowing mix of the tiniest building blocks of matter. This strange early state of the universe is called plasma, a superhot soup made of particles so small we can't even see them with the strongest microscope. This early chapter in the story of the universe is one of the most important. It acts as a bridge between the wild, extreme conditions right after the Big Bang and the moment when the very first atoms, the building blocks of everything we know, started to form. To truly understand how stars, galaxies, and eventually life came to exist, we first need to understand this unusual phase of plasma, where the basic ingredients of matter were made and the rules of physics as we know them began to take shape. Right after the Big Bang, within just the first tiny fraction of a second, the universe was not calm or quiet. Instead, it was a boiling cauldron of energy and heat, where nothing like we know could survive. If we look closely at the moment just after the inflationary period, a time when the universe expanded faster than the speed of light, or even after the mysterious Planck period, when all the forces of nature were still combined, what we see is astonishing. There was no empty space, only a swirling storm of extreme heat and pressure. The temperature of the universe was not just hot, it was billions to trillions of degrees Celsius, far hotter than the center of any star that has ever existed. At such temperatures, atoms couldn't exist. Even the tiny cores of atoms would be ripped apart instantly. Instead, the universe was filled with plasma, a state of matter in which particles are so hot they carry electric charges. But this was no ordinary plasma. It was not like the plasma we see in neon lights or lightning bolts. It was far more unusual and intense. It was made up of protons, neutrons, electrons and their antimatter partners, plus an enormous number of photons, the particles that make up light. In this early plasma-filled universe, energy was packed into every corner. Everything was so tightly squeezed together and so fiercely hot that particles were constantly colliding, changing form, and creating new ones. Light, or photons, had no space to move. Every time a photon tried to travel, it would crash into another particle, usually an electron, and bounce off or get absorbed. The universe was completely opaque, like being inside a glowing fog so thick that light couldn't get through. No matter how hard it tried, light could not escape. Even if an atom somehow started forming, the energy of nearby photons was so strong that it would instantly knock electrons away, breaking the atom apart again. This back and forth, atoms forming and then being destroyed, kept the universe in a chaotic plasma state for a long time. To understand what was happening, we need to talk about the four main forces of nature. These forces control everything in the universe. Gravity pulls things together and shapes galaxies, stars, and planets. Electromagnetism deals with electricity, magnetism, light, and the forces between charged particles. The strong nuclear force holds together the parts of an atom's nucleus, protons and neutrons. The weak nuclear force is responsible for some kinds of radioactive decay and particle interactions. But in the earliest moments, these forces were not separate like they are today. Scientists believe they were all part of a single superforce. As the universe expanded and cooled, this superforce started to split into the separate forces we know now. First, gravity separated during the Planck period. Then the strong force split off, followed by the division of the electroweak force into the electromagnetic and weak nuclear forces. The order and timing of these separations were extremely important. They determined how particles would behave and combine in the plasma that followed. In the very beginning, during the first few millionths of a second, the universe was too hot for even protons and neutrons to exist. Instead, it was filled with a kind of plasma made of quarks, the particles that make up protons and neutrons, and gluons, the tiny particles that hold quarks together. This quark-gluon plasma was unlike anything we see today. Quarks and gluons moved freely, colliding, bouncing, and exchanging energy at unimaginable speeds. It was not until the universe cooled to about 1 trillion degrees Celsius that the strong nuclear force became strong enough to hold quarks together into stable particles, protons and neutrons, in a process called hadronization. As the universe continued to cool, a very strange and important event happened: a fight between matter and antimatter. In those early moments, every time a particle of matter, like a quark or an electron, was made, an equal amount of antimatter, like an antiquark or a positron, was also made. But matter and antimatter destroy each other when they meet. When they do, they disappear in a flash of energy, usually as light. If the universe had made exactly equal amounts of matter and antimatter, they would have completely cancelled each other out. Nothing would be left: no stars, no galaxies, no planets, and no people. But for some reason, there was a tiny imbalance. For every 1 billion particles of antimatter, there were about 1,000,000,001 particles of matter. That tiny extra bit of matter, just one extra particle in a billion, is what survived. Everything we see in the universe today, from the smallest grain of sand to the largest galaxy, comes from that tiny leftover. After the protons and neutrons formed, the universe entered a new phase called the lepton epoch. During this time, the universe was still extremely hot and full of energy, but now it was dominated by leptons, particles like electrons, positrons and neutrinos, as well as photons. Eventually, electrons and positrons began to destroy each other, just like quarks and antiquarks had earlier. Once again, a tiny extra number of electrons survived, and these are the same electrons that make up the atoms in your body today. Neutrinos, on the other hand, are very different. They hardly interact with anything. During this period, they slipped away from the rest of the plasma, spreading through the universe in a quiet, ghost-like wave. This wave is called the cosmic neutrino background, and although it is still around us today, it is extremely hard to detect. At this stage, the number of protons compared to neutrons was also set, which would later determine how the first atomic nuclei were made in the next big phase, nucleosynthesis. For a very long time, from about 10 seconds after the Big Bang to about 380,000 years, the universe was in what scientists call a radiation-dominated era. This means that most of the energy in the universe came from photons, not from matter. As the universe expanded, the light particles stretched out, their wavelengths getting longer and their energy decreasing. But during this long period, these powerful photons kept everything ionized. They had so much energy that atoms could not hold on to their electrons. This is why the universe stayed in a plasma state for so long. It was just too hot and too energetic for stable atoms to form. Eventually, though, the universe cooled enough for electrons to finally join with protons and neutrons, forming neutral atoms. When this happened, light could finally move freely, and the universe became clear for the first time. That moment is called recombination, and it opened the door for the next chapters in the universe's story: galaxies, stars, planets, and life itself. But it all began with a storm of fire, light, and particles, a plasma-filled universe glowing in the darkness, setting the stage for everything that was to come. One of the most important events in the early life of the universe happened during a brief but crucial period, when the cosmos was still extremely hot and filled with a thick glowing soup of particles. This event is called primordial nucleosynthesis, also known as Big Bang nucleosynthesis, or BBN for short. It happened when the universe was only between 3 and 20 minutes old, just moments after the Big Bang. By this point, the temperature of the universe had dropped from unimaginable extremes to about 1 billion degrees Celsius. That's still incredibly hot, hotter than the core of any star, but it was finally cool enough for something amazing to begin: the fusion of basic particles. Protons and neutrons, which had been moving freely, could now start sticking together. This fusion process created the very first atomic nuclei. The first of these was deuterium, a special kind of hydrogen that has 1 proton and 1 neutron in its nucleus. Deuterium acted like a stepping stone. Once it formed, it quickly combined with other particles to create helium-3 and helium-4, both of which are different forms or isotopes of helium. A tiny amount of another element called lithium-7 was also made. However, the universe was cooling too fast. There wasn't enough time for heavier elements like carbon or oxygen to form during this phase. The universe had to wait much later, inside stars, for those to be made. The amounts of these light elements formed during BBN were not random. They depended very precisely on how many protons and neutrons were around, and how dense the universe was with ordinary matter, the kind that makes up atoms, planets, and people. Amazingly, when scientists today measure the amounts of hydrogen, helium, and lithium in the universe, their observations match almost perfectly with what Big Bang nucleosynthesis predicts. This amazing match is one of the strongest proofs that the Big Bang theory is correct. Throughout all of this, from the time when the universe was still a sea of quarks and gluons, to the period of nucleosynthesis, the universe stayed completely opaque, like a room filled with thick glowing fog. That's because electrons had not yet joined with atomic nuclei to form full atoms. These free electrons moved about, constantly bumping into photons, the tiny particles that carry light. Because of this, light could not travel very far. Any beam of light would scatter almost immediately by an electron, like a flashlight trying to shine through dense smoke. This constant scattering meant the universe was filled with a hot, glowing fog made of charged particles and light, a place where light simply couldn't escape or travel freely. This is a key feature of what we call the early universe plasma. Eventually, something amazing happened. Around 380,000 years after the Big Bang, the universe had grown bigger and cooled down even more. Its temperature had dropped to about 3000 Kelvin, which is similar to the surface temperature of a fairly cool star. This cooling caused a very important change. The energy of the photons, the particles of light, was now too low to keep pulling electrons away from atomic nuclei. Finally, electrons could settle down and join with protons and helium nuclei, forming complete neutral atoms. This process is called recombination, though ironically it was the first time these particles actually combined, not a recombination. With electrons now safely locked into atoms, there were far fewer free charged particles for photons to bounce off. Suddenly, light was free. Photons could finally travel long distances without being blocked. This is called photon decoupling, and it opened up the universe in a completely new way. The light from that moment still exists. It has stretched out and cooled, but we can detect it today as the cosmic microwave background. This ancient glow is like a baby photo of the universe. It gives us a direct look at what the cosmos was like when it first became clear. The cosmic microwave background is not perfectly smooth. It has tiny ripples, small differences in temperature. These little irregularities are the very first small clumps of matter, the seeds of galaxies. Over billions of years, gravity pulled more and more matter into these clumps, forming stars, galaxies, and the vast cosmic web we see today. This big change, from a thick glowing fog to a clear cosmos, marked the end of the radiation-dominated time and the start of the matter-dominated time. But even though light could now travel freely, there were no stars yet, no bright objects lighting up the universe. This led to a mysterious period called the Cosmic Dark Ages, when the universe was quiet and dark, waiting for gravity to gather the first stars into being. In this way, the early universe plasma acted like a cosmic forge, a place where the basic particles were formed, the main forces began to separate, and the first conditions were set for the birth of everything we know. From chaos and fire came order, light, and eventually life. Imagine the universe just moments after the Big Bang. It was unbelievably small, extremely hot, and growing at a speed beyond anything we could ever imagine. Now picture this. In the blink of an eye, the universe expanded faster than the speed of light, something so amazing that it changed everything in the universe. This fast growth is what scientists call cosmic inflation. It's one of the most exciting and tricky ideas in all of cosmology because it explains how our universe went from being an almost invisible speck of matter to the huge, organized cosmos we see today. Without this idea, many parts of the universe wouldn't make sense at all. To fully understand inflation, we need to go back in time, way back to just after the Big Bang. Picture this moment called Planck time, which happened around 1/4 of a second after the Big Bang. At this point, the universe was tiny, so small that it might have been smaller than a proton. But then, something amazing happened. In an incredibly short time, the universe began to grow at a shocking rate. This is where the story of cosmic inflation begins. Cosmic inflation is the idea that in the first few fractions of a second after the Big Bang, specifically between 1/300,000th of a second and 1/1000th of a second, the universe expanded at an incredible pace. During this time, the universe grew extremely fast. To imagine this, think of taking something as small as an atom and stretching it to the size of an entire galaxy in less time than it takes to blink. That's the power of inflation. It made the universe grow by at least 100 quintillion times. Now, don't think of this as an explosion. This wasn't like fireworks or matter flying apart in all directions. Instead, it was space itself stretching and growing. The space between galaxies, stars, and particles grew faster than light, and even though this sounds impossible, it is actually allowed by the rules of physics. Because it's not matter moving faster than light, it's the space itself that is growing. And space, as strange as it seems, doesn't have the same limits that objects moving through space do. Inflation did more than just make the universe grow quickly. It helped solve some of the biggest puzzles in cosmology, things that would otherwise be hard to explain. For example, if you look at the night sky, the stars may seem scattered randomly across the universe. But if you zoom out far enough and take a bigger view, you'll see something surprising. No matter where you look, the universe looks mostly the same. The cosmic microwave background radiation, the faint glow left over from the Big Bang, is almost exactly the same temperature everywhere. This is where things get interesting. You might think that the universe, if it started from an extremely hot, dense point, should have areas that are very different from each other, especially when those areas are billions of light years apart. How could two far-off parts of the universe be so similar in temperature and makeup? This is a puzzle called the horizon problem. According to the usual Big Bang idea, there hasn't been enough time for light or heat to travel between these faraway areas to make them similar. Without inflation, these distant areas should look very different, with some places much hotter or colder than others. But inflation solves this problem. By stretching space so fast, it allowed far-off areas to be in contact with each other in a way that evened out the temperature and matter. During a period of inflation, the universe grew at an extremely fast rate. This fast stretching was so big that areas of space that were once close together were moved far apart. Imagine this. Before inflation, all parts of the universe were connected, like different parts of a crowded room. They shared the same temperature and conditions, and that's why even today, no matter how far apart different parts of space are, they look very similar. This fast growth of the universe also helps smooth out early bumps. Picture a balloon with little lumps all over it. If you blow up that balloon really fast, those tiny lumps get stretched out and smooth over, right? Well, that's similar to what inflation did for the universe. It took a universe full of small bumps, tiny wrinkles in space, and stretched them so far apart that they became smooth and even. Not only did inflation make the universe more even, but it also gave us clues about how galaxies and stars formed. The fast growth of the universe helped set the stage for what we see today. Clusters of galaxies, stars, and planets spread across space. But you might be wondering, that sounds amazing, but is there any proof that inflation actually happened? And that's where it gets even more exciting. While inflation is still seen as an idea, there's a lot of strong evidence to support it. A big piece of this evidence comes from something called the cosmic microwave background, CMB, the earliest light we can detect from the universe. The CMB acts like a picture of the universe when it was just 380,000 years old, which is very young compared to its current age of about 13.8 billion years. Scientists study the CMB to understand what the early universe was like. and it's in this ancient light that we find important clues about inflation. One of the most important predictions of inflation is that there were tiny changes, microscopic ripples in space and time, happening during the fast growth. Even though the universe was expanding quickly, these tiny changes called quantum fluctuations still happened. They were small, but as the universe grew, these changes stretched out to become big enough to influence the formation of galaxies, stars, and planets. Over time, these changes left a mark on the cosmic microwave background. When scientists look closely at the CMB, they can see tiny temperature differences, which are the leftover signs of those early changes. Without inflation, these differences would be much bigger or may not exist at all. But because the predictions from inflation match what we see in the CMB so closely, it's like finding a fingerprint left behind by the early universe, showing that inflation really happened. But that's not all. There's another puzzle that inflation helps solve: the flatness of the universe. When scientists study the overall shape of the universe, they find that it's almost perfectly flat. By flat, we don't mean it's like a flat piece of paper. It means that space isn't curved or bent like a ball or stretched like a saddle. Space seems to follow the rules of normal flat geometry, even when we look at the largest areas. Now, here's the puzzling part. If the universe had started randomly, it would have likely been either curved or warped. So how did it become so flat? This is where inflation helps. The universe grew so fast that on the larger scales, it became nearly perfectly flat. When we measure the shape of the universe today, we find that it is indeed flat, just as inflation predicted. Let's look more closely at how inflation played an important role in the creation of galaxies and the structure of the whole universe. We've already talked about the tiny quantum fluctuations, those tiny, almost invisible ripples that existed in the early universe. These changes weren't just random noise, they were actually key to the formation of everything we see today. During inflation, these tiny ripples in space were stretched across the universe in an instant. It's like stretching a tiny piece of fabric to cover an entire room in the blink of an eye. Over time, these changes grew bigger, and as the universe continued to cool, they formed the first small clumps of matter. As the universe cooled more, these clumps of matter began to fall together under their own gravity. This process eventually led to the formation of the very first stars and galaxies. This is how the large-scale structure of the universe started to take shape. The way galaxies are spread out across huge distances in clusters and long, complex filaments matches what we would expect if inflation happened. The tiny ripples from that early inflation were the seeds that grew into the galaxies and stars we see today. So, when we look at the huge cosmic web of galaxies across the universe, we are seeing the direct result of those tiny early ripples that were stretched out during inflation. Without inflation, it's hard to explain how the universe got this structure. The way galaxies are placed today, how they form clusters, and how they're connected by huge filaments, it all fits perfectly with inflation. Inflation didn't just help form galaxies, it also explains the evenness of the universe, while still allowing for tiny imperfections. These tiny imperfections, though small at first, slowly grew into the stars, galaxies, and everything we know in the universe today. So, what exactly is cosmic inflation? Imagine the universe in the first split second of its life, before galaxies, stars, or even atoms could form. In that moment, the universe grew at an unbelievable speed, faster than we could imagine. This growth happened in the blink of an eye, setting everything in motion that led to the universe we know now. Inflation is the process that explains how the universe grew so big, so flat, and so even in the beginning. But it didn't just create evenness. It also gave rise to the small changes that would eventually become galaxies and stars. Even though inflation is still seen as an idea, there is strong evidence supporting it. We can see its fingerprints everywhere, from the cosmic microwave background, the afterglow of the Big Bang, to the large-scale structure of the universe. All around us there are traces of that ancient inflationary event. It's a reminder that, right from the very beginning, powerful cosmic forces were already shaping the universe, preparing the way for everything that came afterward.